Imagine standing in a footprint. Not just any footprint, but one so enormous you could lie down inside it, curled up like you're sleeping, and still not touch the edges. A single step frozen in stone, left behind by a creature whose shoulder stood higher than a 2-story building, whose weight, pressing down into ancient mud 95 million years ago, was enough to leave a mark that would outlast everything, outlast the animal itself, outlast the world it walked through, outlast the extinction that erased it from the earth. This footprint is real. It exists. You can go see it if you want, though honestly that's not why I'm telling you about it. I'm telling you because that print, that one step, is the doorway to the most astonishing story in the history of life on land. The story of the giants. The real giants. Not myths, not legends, but animals that actually existed, that shook the ground beneath them, that lived and breathed and moved through forests and floodplains we can barely imagine today. We're going on a journey tonight, a long, slow walk backward through hundreds of millions of years. We're going to meet the largest creatures that ever walked the earth, sauropods with necks like construction cranes, armoured titans weighing more than a dozen elephants, mammals the size of houses that grazed on grass after the dinosaurs were gone, and we're going to uncover the mystery at the heart of it all. What allowed life on land to reach such staggering, impossible proportions? And what forces, what catastrophes, what slow unravelling of ecosystems conspired to bring every single one of them down? By the time we're done, you'll have walked alongside the biggest animals that ever lived on solid ground, and you'll know why nothing like them may ever walk again. If you're here to fall asleep, you're in the right place. That's exactly what this is for, so get comfortable. Let the ancient world wash over you like a slow tide. And maybe, if you feel like it, leave a comment and tell me where you are and what time it is. I check them all. Tokyo at dawn, London at midnight, São Paulo during lunch. Is like the whole world tuning in at once, all of us drifting back together into deep time. Now, back to that footprint. The creature that made it probably stood about 7 meters tall at the shoulder, maybe more. That's roughly 23 feet. Picture a giraffe, then picture something twice as tall, 4 times as heavy, with a neck stretching out another 10 or 15 meters ahead of it, and a tail just as long sweeping behind. Its limbs were thick as tree trunks, built to carry a body mass somewhere between 60 and 80 metric tons. Some scientists think certain individuals may have pushed past 100 tons, though that number is still debated. Either way, we're talking about an animal heavier than the largest blue whale ever measured. Except this animal lived on land. It walked. It breathed air. It moved through forests of ferns and conifers and later, the first flowering plants. And when it stepped, the earth remembered. We know this not just from one footprint, but from trackways. Long parallel rows of prints stretching across ancient riverbeds and mudflats, now turned to stone. Some trackways show dozens of individuals moving together, families maybe, herds crossing soft ground in search of food or water. You can see where the juveniles walked between the adults. You can see where one animal paused, shifted its weight, then kept moving. These were not monsters. They were animals. They had lives, routines. They ate, they slept, they raised their young. For over 140 million years, creatures like this dominated the planet in a way nothing has since. And then, in a geological instant, they were gone. Tonight we're going to find out how they got so big, how we know what we know about them, even though many are reconstructed from just a handful of bones, what it was like to live in their world, and why, after ruling the earth longer than mammals have even existed, every single one of them vanished. The story starts long before the giants, back when life on land was still learning how to be big at all. Let's go back, way back. Before we meet the giants, we need to go back to a time when nothing on land was giant at all. when the very idea of a 70-ton animal walking around on four legs would have seemed impossible, because the largest things moving across solid ground were barely the size of your forearm. This is the late Paleozoic, roughly 350 to 250 million years ago. The continents don't look like the maps you know. North America and Europe are joined into one landmass called Laurussia. Gondwana, the southern supercontinent, includes what will one day become Africa, South America, Antarctica, Australia and India all fused together. Between them, shallow tropical seas stretch for thousands of miles, and on the edges of these seas in vast swampy lowlands, life is conducting one of the most important experiments in its history, learning to live entirely on land. The first vertebrates to crawl out of the water, the early tetrapods, were not impressive by our standards. Creatures like Poderpes, walking the shores of early Carboniferous Scotland around 348 million years ago, measured maybe a metre long, stubby-limbed, flat-headed, spending most of their time half-submerged. They hugged the ground because they had to, their limbs splayed out to the sides like a lizard's, not tucked underneath like a dog's or a horse's. Every step was a struggle against gravity. They were still in many ways more fish than land animal, still tied to the water for reproduction, for moisture, for safety. But the world they were inheriting, that swampy Carboniferous world, was like nothing before or since. Picture this: endless wetland stretching across what will one day be the coalfields of Pennsylvania, Illinois, Scotland, Poland. Forests, but not forests like you know. These are forests of giant club mosses, lepidodendron, rising 30 metres into the humid air, their bark covered in diamond-patterned scales. Towering horsetails, calamites, thick as telephone poles, tree ferns spreading their fronds over black water that never quite dries. The air is thick, warm, heavy with moisture. When it rains for days. When the sun breaks through, it bakes the swamps into a humid haze that hangs between the trees like fog. And the air itself is different, richer, denser. Atmospheric oxygen levels during the late Carboniferous reached somewhere around 30 to 35%. Today, it's 21%. That extra oxygen changed everything. It allowed fires to burn hotter, faster. It allowed metabolism to run at higher intensities. And most strikingly, it allowed something that had never happened before: giant insects. Flying through the canopy of those ancient swamp forests were creatures that would make you stop and stare if you saw them today. Dragonfly-like griffin flies called Meganeura, with wingspans stretching 70 centimetres across. That's about the length of your arm from shoulder to fingertip. They weren't true dragonflies, but close relatives, and they hunted like aerial predators, snatching smaller insects out of the air with spiny legs, their enormous compound eyes tracking movement through the dappled light, filtering down through the fern canopy. There were millipedes the size of crocodiles crawling through the leaf litter, scorpions 1/2 metre long. These were the first large animals to truly dominate the land, and they were arthropods, not vertebrates. The insects got there first. Why so big? The leading explanation ties back to that oxygen-rich atmosphere. Insects don't breathe with lungs. They use a system of tubes called tracheum that carry oxygen directly to their tissues through passive diffusion. In normal air, this system hits a limit. The tubes can only work efficiently up to a certain body size before the insect suffocates under its own mass. But in an atmosphere with 30% oxygen, those tubes could supply much larger bodies. Natural selection favoured size, especially among predators. Bigger meant faster, stronger, capable of taking down larger prey. For maybe 50 million years, these giant arthropods ruled the land while vertebrates stayed relatively small, still figuring out how to walk properly, still vulnerable, still stuck near the water. But things were changing. The climate was shifting. The endless swamps were beginning to dry out as the continents drifted and collided. By the time the Permian period arrived, around 299 million years ago, the world looked different. The coal swamps were gone, replaced by vast interior plains and seasonal river valleys. Conifers and seed ferns spread across drier ground. Volcanic mountain ranges pushed up along the edges of the colliding continents. The supercontinent Pangaea was taking shape, all the land on Earth grinding together into one massive block that stretched from pole to pole. And in the interior of Pangaea, far from any ocean, conditions became harsh. Hot summers, cold winters, seasonal droughts. This was no longer the humid, stable greenhouse of the Carboniferous. This was a world of extremes. The animals changed with it. Early reptilian lineages, the amniotes, began to radiate and diversify. Unlike amphibians, they could lay eggs with protective shells. They didn't need to return to water to breed. This freed them to move inland to colonize the drier uplands and plains where their amphibian ancestors couldn't survive. Some of these early reptiles stayed small and lizard-like, but others grew. Not huge, not yet, but larger than anything before. Stocky herbivores like the casids, distant cousins of mammals, developed barrel-shaped bodies to house the massive guts needed to digest tough plant material. Some reached lengths of 3 or 4 meters and weights approaching a ton. Predatory snapsids prowled after them, developing longer legs, more efficient gaits, the beginnings of the adaptations that would eventually lead to mammals. And scattered among them, easy to overlook, were small, agile reptiles called diapsids. Slender bodies, long tails, quick darting movements. They didn't dominate. They weren't the biggest or the most common, but they carried in their bodies the genetic toolkit that would one day build the largest land animals in the history of Earth. These were the ancestors of the archosaurs, the lineage that would give rise to crocodiles, pterosaurs, and dinosaurs. But first, the world had to end. Around 252 million years ago, something went catastrophically wrong. In what is now Siberia, deep beneath the Earth's crust, a plume of superheated mantle rock punched through the surface. Lava poured out across an area the size of Western Europe, not in explosive eruptions like Mount St. Helens, but in massive, sustained flood basalt flows that went on for hundreds of thousands of years, maybe longer. This is the Siberian Traps, and it was one of the largest volcanic events in Earth's history. The lava itself wasn't the main problem. The problem was what came with it. Carbon dioxide, sulfur dioxide, methane, toxic gases pouring into the atmosphere in unimaginable quantities. Global temperatures spiked, oceans acidified, oxygen levels in the water plummeted, creating vast dead zones where nothing could survive. On land, the warming triggered wildfires, droughts, and the collapse of plant communities that had taken millions of years to develop. The extinction that followed is called the Permian Triassic extinction, but most paleontologists just call it the Great Dying. Roughly 70% of all terrestrial vertebrate species vanished. Maybe 80% of genera. In the oceans, it was even worse. Somewhere between 80 and 90% of all marine species went extinct. Entire groups of animals that had dominated for tens of millions of years simply disappeared. Trilobites, gone. Blastoid echinoderms, gone. Whole orders of corals, brachiopods, bryozoans, wiped out. This was the worst mass extinction in Earth's history. Far worse than the asteroid impact that would one day kill the dinosaurs. Life came closer to complete annihilation during the Permian Triassic extinction than at any other time we know of. But life didn't end. It never does. It persists. It adapts. It fills the empty spaces left behind. In the aftermath, the world was a desolate place. The early Triassic, The few million years immediately following the extinction shows a planet struggling to recover. Low diversity, simple ecosystems. The surviving animals were mostly small, generalized, capable of eating whatever they could find. The giants of the Permian were gone. The giant insects, already in decline as oxygen levels fell and new predators appeared, dwindled further. For a while, nothing big walked the earth, but in that emptiness, opportunity, ecological niches left vacant by the extinction, waiting to be filled. And among the survivors, one group was poised to take advantage, the archosaurs, those small, quick, unassuming reptiles from the late Permian. They had survived, maybe because of their agility, their efficiency, their ability to regulate body temperature better than many of their competitors. And now, in a world swept clean of the dominant herbivores and predators that had kept them in check, they began to grow, to diversify, to experiment with new body plans, new ways of moving, new strategies for finding food and avoiding danger. Within 20 million years, archosaurs would dominate terrestrial ecosystems. Within 50 million years, some of their descendants would be the size of buses, and within 100 million years, they would include animals so large, so impossibly massive, that we're still struggling to understand how they even existed. The age of giants was about to begin, but it started here, in the ashes of the worst catastrophe life had ever faced, with creatures small enough to hold in your hand. Evolution doesn't know where it's going. It only knows survival, and sometimes survival leads to something no one could have predicted. The archosaurs were about to inherit the Earth. The Triassic world that emerged from the Great Dying wasn't just recovering, it was transforming into something fundamentally new. Picture the Earth around 235 million years ago. All the continents are still locked together in Pangaea, that massive supercontinent stretching from pole to pole. But this isn't the swampy, humid world of the Carboniferous. This is something harsher. The interior of Pangaea, thousands of miles from any ocean, has become a vast desert belt, hot, dry, intensely seasonal. Monsoons dump torrential rains during brief wet seasons, turning dry riverbeds into raging torrents. Then for months, nothing. Just scorching sun, cracked earth, and winds carrying red dust across endless plains. The rocks tell the story. Across what are now Arizona, Argentina, Morocco, Germany, you find thick layers of red sandstone, ancient sand dunes frozen in stone, salt deposits left by evaporating lakes. This was a world of extremes. Summer temperatures in the interior could reach 40 degrees Celsius or higher. Winters, especially at higher latitudes, brought cold snaps that would have killed anything not adapted to endure them. Life clustered near the coasts, in river valleys, anywhere water could be found reliably. The deep interior remained largely empty, too harsh for most creatures to colonize permanently. But along those river valleys, in those scattered forests of conifers and seed ferns and cycads, something remarkable was happening. The archosaurs were splitting, diverging, experimenting with different strategies for survival in this brutal new world. One branch, the Pseudosuchians, gave rise to the crocodile lineage. But in the Triassic, they weren't lurking in rivers waiting for prey. Many were fully terrestrial predators. Some walked upright on their hind legs like tiny tyrannosaurs. Others developed armor plating and herbivorous lifestyles. They were successful, diverse, dominant across many ecosystems. For most of the Triassic, if you wanted to point at the ruling reptiles, you'd point at the crocodile line archosaurs. The other branch, the Avmatate Arsalians, was quieter, more experimental. This lineage split again, producing two groups that would change the world. One gave rise to pterosaurs, the first vertebrates to achieve powered flight. launching themselves into an aerial realm that had belonged exclusively to insects for over 100 million years. The other group, easy to miss at first, small and unassuming, were the dinosaurs. The earliest dinosaurs we know appeared in the late Middle Triassic, roughly 230 to 235 million years ago, in what is now South America. Creatures like Eoraptor, discovered in the Badlands of northwestern Argentina. If you could see one alive, you might mistake it for a large lizard at first glance, about 1 meter long from nose to tail tip, maybe 1.5 meters if you found a particularly large individual. Lightly built, weighing perhaps 10 kilograms, about the size of a medium dog. It walked on its hind legs, bipedal, with forelimbs much shorter than the legs. Quick, agile. Probably an omnivore, capable of eating whatever it could catch or scavenge. Plants, insects, small vertebrates, whatever the harsh environment provided. Herrerasaurus was larger, maybe 3 to 6 meters long, a more committed carnivore with sharp teeth and grasping hands tipped with claws. But even this predator was modest by the standards of what would come later. It weighed perhaps 200, maybe 350 kilograms, about the mass of a large lion, but stretched out longer and leaner. These early dinosaurs weren't dominant. They weren't the top predators. They weren't the most common herbivores. They were niche players in ecosystems still ruled by other archosaurs and various holdover reptile groups from the Permian. But they carried something special, an anatomical revolution encoded in their skeletons. Most reptiles before them, and many reptiles alongside them, moved with sprawling gaits. Legs splayed out to the sides, elbows and knees bent, bellies low to the ground. This works fine for short bursts or ambush hunting, but it's metabolically expensive for sustained movement. Every step requires lifting the body against gravity while also pushing forward. It's exhausting. Dinosaurs moved differently. Their legs were positioned directly underneath their bodies, vertical like pillars, hips designed to hold the legs in this upright posture, ankles that worked like hinges, swinging forward and back in a straight line, not twisting sideways. This erect limb posture is mechanically efficient. It turns the legs into columns supporting the body's weight with minimal muscular effort. Energy that would have been wasted fighting gravity could now be used for endurance, for speed, for growth. Their bones were different too. Hollow. Not completely hollow like a bird's, not yet, but thin-walled, with internal struts and air spaces that reduced weight without sacrificing strength. This matters more than it might seem. Lighter bones mean less energy needed to move them. Less energy per step means you can walk farther, run longer, forage more efficiently. Over millions of years, these small advantages compound, and they had lungs, respiratory systems that evidence suggests were more efficient than typical reptile lungs. Not quite the flow-through air sac system of modern birds, but something intermediate, something better at extracting oxygen from each breath. This meant higher metabolic rates, more sustained activity, the ability to grow faster and maintain body temperature more effectively in the temperature extremes of Triassic Pangaea. None of this made them giants, not yet. These features were survival adaptations for small animals living in harsh environments. But they laid the foundation. They created a body plan that could be scaled up in ways no other land vertebrate had managed before. By the late Triassic, some dinosaur lineages were beginning to explore that potential. The sauropodomorphs, the group that would eventually produce the largest land animals in Earth's history, started small. Early members like Saturnalia from Brazil were barely 2 meters long, maybe 5 kilograms, probably still capable of walking on their hind legs when they wanted speed. But they had begun to shift toward herbivory, developing slightly longer necks, teeth better suited for cropping vegetation, guts capable of fermenting plant matter. Then came Plateosaurus. Not huge by later standards, but startling for its time. 7 to 10 meters long depending on the individual, 2 to 4 metric tons, about the size and weight of a large hippo, but shaped completely differently. Long neck, long tail, massive hind legs, shorter but powerful forelimbs tipped with a large thumb claw, possibly for defense or stripping vegetation. Some individuals may have walked on all fours when moving slowly, rearing up on hind legs to reach higher branches or intimidate rivals. Plateosaurus fossils are found across late Triassic Europe, in what are now Germany, Switzerland, France, Greenland. Dozens of individuals preserved, some in mass accumulations that suggest they gathered in groups near water sources, maybe herds congregating during dry seasons and getting caught in flash floods when the rains finally came. Bone studies show they grew rapidly, continuously, more like mammals or birds than modern reptiles. Some individuals reached full size in perhaps 12 to 20 years. Others kept growing longer, reaching larger sizes, flexible growth patterns that could adjust to food availability. This was an experiment, an early test of how large a terrestrial herbivore could become using the new dinosaur body plan, and it worked. Plateosaurus wasn't just surviving, it was thriving across multiple environments, from river valleys to upland forests, a hint, a preview of what the dinosaur lineage was capable of achieving. But the Triassic wasn't finished with extinctions. Around 201 million years ago, as the Triassic gave way to the Jurassic, volcanism erupted again. Not in Siberia this time, but along the seams where Pangaea was beginning to fracture. The Central Atlantic Magmatic Province, a massive flood basalt event as the continent started to pull apart, opening what would eventually become the Atlantic Ocean. Lava flows covering hundreds of thousands of square kilometers, volcanic gases flooding the atmosphere, carbon dioxide levels spiking, temperatures soaring, then possibly plunging as sulfate aerosols from the eruptions reflected sunlight and triggered brief but intense volcanic winters. The end-Triassic extinction wasn't as severe as the Permian catastrophe, but it still killed perhaps 70 to 80% of species. The victims included many of the large crocodile-line archosaurs that had dominated Triassic ecosystems, many of the holdover reptile groups from earlier eras, whole families of marine reptiles and reef-building organisms. The dinosaurs survived. Not all of them, but enough. And when the volcanic winter ended, when temperatures stabilized and rainfall patterns shifted, when the ash settled and new forests began growing in soil enriched by volcanic minerals, the dinosaurs emerged into a world swept clean of their main competitors. The Jurassic was beginning, and this time the dinosaurs wouldn't be bit players, they would be the stars. Within a few million years, descendants of modest creatures like Plateosaurus would grow to sizes that strained the limits of what physics allowed on dry land. The age of giants was about to truly begin, and the world would never see anything quite like it again. The Jurassic world was wetter, warmer, greener than anything the Triassic had offered. Pangaea continued its slow-motion breakup, rifting along the seams where volcanic fires had burned. The supercontinent was splitting into two massive pieces, Laurasia in the north, Gondwana in the south, with a seaway called Tethys gradually widening between them. This tearing apart of continents had consequences. New ocean basins forming, seafloor spreading, global sea levels rising, flooding low-lying continental margins, creating vast, shallow seas that extended hundreds of miles inland. All that new coastline, all that ocean surface meant more evaporation, more rainfall, more moisture cycling through the atmosphere. The brutal Triassic deserts retreated. The climate grew milder, more stable. Not everywhere, not all at once, but across much of the planet, rainfall became more reliable. Seasonal monsoons less extreme. Temperature gradients from equator to poles remained weak. Evidence suggests the poles were ice-free, with sea surface temperatures even at high latitudes hovering around 20 degrees Celsius. The deep ocean waters were only a few degrees cooler. This was a greenhouse world, warm and humid, with no polar ice caps to lock away moisture, no frozen wastelands to interrupt the flow of life. Forests expanded. Conifers dominated the canopy. Araucarias, relatives of the modern monkey puzzle tree. Podocarpus, ancient cypresses. Below them, an understory of tree ferns with fronds spreading like green fans, cycads with thick trunks and palm-like crowns, ginkgos, seed ferns, horsetails growing in dense thickets along riverbanks. This wasn't flowering plant diversity yet, no grasses, no roses, no oaks, but it was lush, productive, green layered on green, capturing sunlight and converting it into biomass at scales the recovering Triassic ecosystems had only begun to approach. And into this botanical abundance the sauropods exploded. By the late Jurassic, roughly 155 to 145 million years ago, they had become the dominant large herbivores across much of the world. The Morrison Formation of western North America preserves one of the richest windows into this age. Sediments laid down across what are now Colorado, Wyoming, Montana, Utah, New Mexico. Ancient floodplains, meandering rivers, shallow lakes, fern prairies stretching between gallery forests of conifers. The climate here was semi-arid, evidence suggests, with seasonal rainfall. Dry periods followed by floods, but even in these relatively harsh conditions the sauropods thrived. Diplodocus moved through these landscapes like living bridges, 25, maybe 27 meters from nose to tail tip, but surprisingly light for their length, perhaps only 10 to 20 metric tons, about as much as 3 or 4 large elephants despite being almost 5 times longer. Their bodies were long and low-slung, necks stretching forward, tails extending behind, tipped with a thin whip of vertebrae that some paleontologists think could crack like a bullwhip, producing sonic booms to communicate or intimidate. Their teeth were concentrated at the front of long horse-like skulls, peg-shaped, designed for stripping leaves and fronds, not for chewing. They would have spent most of their waking hours eating, sweeping those long necks through the vegetation, cropping, swallowing, moving on. Bone beds preserve multiple Diplodocus individuals together, suggesting they moved in groups, maybe small herds, family units possibly. Walking through the fern meadows in the early morning, dew still clinging to the fronds. The ground would have trembled with each step, not violent shaking, but a deep, rhythmic vibration. 60 tons of sauropods spread across a herd of 4 or 5 individuals, each footfall compressing the earth, a slow drum beat that other animals would have felt as much as heard. Apatosaurus was shorter, but more massive, 20 to 23 meters long, but built more robustly. Thicker limbs, heavier torso. Mass estimates vary, but probably somewhere between 20 and 40 tons for large adults. The name means deceptive lizard, but for decades it was better known as Brontosaurus, thunder lizard, a name that captured something essential about what it must have been like to share a world with them. The confusion arose from early paleontological rivalry, misidentified specimens, scientific names being combined and then later split again. The details matter to specialists, but what matters here is the creature itself. A giant capable of rearing up on its hind legs perhaps, using that massive tail as a tripod, reaching high into the conifer canopy, where other herbivores couldn't follow. Then there was Brachiosaurus, the arm lizard, named for its unusually long forelimbs, longer than the hind legs, giving it a sloping giraffe-like profile. 20 to 22 meters long, perhaps 9 to 12 meters tall if you measured to the top of the head when the neck was fully extended upward. Mass estimates range widely, from around 23 tons to over 40, depending on the assumptions about body density and air sac volume. Either way, enormous, adapted for high browsing. While Diplodocus swept low and Apatosaurus reached medium heights, Brachiosaurus fed from the treetops, cropping the high branches other sauropods couldn't reach, each species carving out a slightly different ecological niche in the same forest. Across the Tethys Ocean, in what is now Tanzania, another giant walked the Tendaguru floodplains, Giraffatitan. Once classified as an African species of Brachiosaurus, but now generally treated as a separate genus. 22 meters long, about 12 meters high at the head. Perhaps 20 to 40 tons or more, the estimates remain uncertain. The Berlin Museum mount, based largely on a single spectacular specimen, has become one of the most famous dinosaur reconstructions in the world, a reference point for understanding sauropod posture and biomechanics. Giraffatitan's bones suggest powerful neck muscles, vertebrae shaped to hold the head high, with minimal energy expenditure, a creature built to spend hours browsing above the reach of competitors. But these giants didn't walk alone. Beneath them, around them, sharing the same floodplains and forests, lived whole ecosystems. Stegosaurus with its back plates and tail spikes, Camptosaurus and other ornithopods, smaller herbivores filling the browsing niches too low for sauropod necks, too high for ground-hugging reptiles. And watching them all, waiting for opportunity, were predators. Allosaurus, 8.5 meters long on average, with large individuals approaching 9 or 10 meters, perhaps 1.5 to 2 tons, not large enough to threaten a healthy adult sauropod directly probably, but young sauropods, sick individuals, animals weakened by injury or drought. These were vulnerable. Allosaurus fossils make up 70 to 75% of all theropod remains in the Morrison Formation, suggesting they were the dominant large predators, apex hunters in an ecosystem where even the predators had to operate on a monumental scale. This was an evolutionary arms race played out over millions of years, predators selecting for speed, power, weapons, prey responding with size, social behavior, defensive strategies, the sauropods growing larger not just because food was abundant, though it was, but because being enormous was itself a defense. Get big enough and nothing can touch you. At 50 tons you're invulnerable except in youth. At 30 tons you need only fear coordinated pack hunters or catastrophic bad luck. The mathematics of predation shift when the prey outweighs the predator by a factor of 20 or 30 to 1. Picture a moonlit night in the late Jurassic. A river delta, silver water reflecting the stars, mist rising from the warm water into cooler air. Along the far bank, silhouettes moving, necks rising above the tree line like living towers. Slow, deliberate. A Brachiosaurus reaching into the canopy, pulling down a branch heavy with needles. Behind it, another shape, smaller but still immense, then another. A family group perhaps, or just individuals drawn to the same rich feeding ground. The moonlight catches on wet flanks. The river murmurs. Somewhere in the distance, the barking call of an Allosaurus, hunting smaller prey through the fern thickets. This moment, multiplied across millions of years, replicated on different continents as Pangaea continued to fragment, was the age of sauropods. Not the end of their story. They would grow larger still, adapting to new climates, new continents, new challenges as the Jurassic gave way to the Cretaceous. But here, in these forests of green and thunder, they established something fundamental. They proved that terrestrial vertebrates could reach sizes that strained the upper limits of what bone and muscle could support on land. The question that still fascinates paleontologists, still drives research and debate, is how. How did they get so large? What biological innovations made such enormity possible? That answer lies deeper than just having enough food or favourable climate. It lies in the architecture of the sauropod body itself, in adaptations so fundamental that without them, nothing resembling these giants could ever have walked the earth. Being enormous wasn't an accident. It was engineering. Every animal that has ever lived faces the same fundamental problem: gravity, the square-cube law. As a body grows larger, its volume and mass increase as the cube of its dimensions, but the cross-sectional area of its bones and muscles only increases as the square. Double an animal's length and you increase its weight 8-fold, but the strength of its legs only 4-fold. Keep scaling up, and eventually the skeleton can't support the mass. The muscles can't move it. The heart can't pump blood through it. Physics sets a limit, an upper boundary beyond which bone breaks and biology fails. Sauropods lived on the far side of that boundary. They were so large that by conventional mammalian engineering they shouldn't have been possible. A 50-ton sauropod isn't just a scaled-up elephant, it's something else entirely. Something that required a complete redesign of how a land animal's body could work. The key was lightness. Not fragility, but structural efficiency carried to an extreme that no other land vertebrate lineage has ever matched. Start with the bones. Sauropod vertebrae weren't solid, they were pneumatic, honeycombed with chambers and hollows that connected to an elaborate system of air sacs extending throughout the body. Hold a sauropod vertebra up to the light, if you could lift one, and you'd see the thin struts of bone forming internal chambers, external cavities, spaces where air flowed through living tissue. Some estimates suggest that in taxa like Sauroposeidon, the massive brachiosaur from early Cretaceous North America, neck vertebrae were more than 75% air by volume. Across different sauropod groups, vertebrae averaged around 60% air, sometimes more. This was weight reduction on a scale that made bipedal walking possible for giants. Made necks 9 meters long mechanically feasible. A solid bone vertebra of the dimensions found in Brachiosaurus or Argentinosaurus would have weighed hundreds of kilograms. Pneumatic, it might weigh half that, maybe less. Multiply that savings across every cervical vertebra, every dorsal, every rib, and you're reducing the mass of the axial skeleton by tons while maintaining structural strength. The pneumatic system wasn't borrowed, it was inherited. Modern birds have the same architecture, air sacs invading their bones, connecting to lungs that work fundamentally differently from mammalian lungs. In mammals, air flows in and out of dead-end alveoli. Tidal breathing, inefficient. A significant fraction of each breath is dead space, air that never reaches the gas exchange surfaces. But in birds, and almost certainly in sauropods, air flows in one direction through the lungs, drawn through by air sacs positioned anterior and posterior to the lung tissue itself. Fresh air enters, passes through the parabronchi where oxygen is extracted, then exits through posterior sacs. Meanwhile, air stored in anterior sacs is being pushed through on the next cycle. Continuous unidirectional flow, vastly more efficient oxygen extraction per breath. For a sauropod, this meant something profound. An animal with a neck stretching 9 or 10 meters from lungs to head, breathing through a trachea that represented enormous dead space, would have suffocated with mammalian lungs. The volume of air needed just to fill the windpipe would have made efficient gas exchange nearly impossible. But with a flow-through system and distributed air sacs, the problem vanished. Air moved continuously. Oxygen reached tissues. The long neck didn't become a respiratory trap. It became a foraging tool with no breathing penalty. There was a thermal advantage too. All that internal airspace, all those sacs distributed through the trunk and neck, provided surface area for heat dissipation. A 50-ton animal generates enormous metabolic heat. Without efficient cooling, core temperature rises, proteins denature, organs fail. Evidence suggests sauropods may have used their pneumatic systems as internal radiators, circulating air through the body, dissipating heat across the vast internal surface area of the air sac membranes. Not proven, but biomechanically plausible, and possibly essential for an animal that couldn't simply jump in a river and stay there all day. Then there was the feeding strategy. Sauropods didn't chew. Their teeth were simple, pegs in Diplodocus, broader and more spoon-shaped in Brachiosaurus, but never the grinding, chewing batteries of hadrosaurs or the shearing carnassials of predators. Instead, they snipped vegetation and swallowed it more or less whole. The real processing happened in the gut, an enormous fermentation chamber, probably located in the lower trunk, where microbial communities broke down cellulose and lignin over days of slow digestion, like a walking compost heap turning tons of low-quality plant matter into usable nutrients through sheer volume and residence time. This strategy did something critical. It kept heads small. A sauropod skull might be 60 centimeters long, less than a meter in the larger species, tiny compared to the body. Camptosaurus, a much smaller herbivore that did chew its food, needed a skull large enough to house the jaw muscles for grinding, heavy, energy expensive to hold up and move around. But a sauropod with simple teeth and no chewing muscles could have a skull that weighed perhaps 50 kilograms instead of 500. At the end of a 9-meter neck, that difference was everything. The mechanical advantage of a lightweight head allowed the neck to evolve longer without collapsing under its own weight. The neck itself became an energy-saving device. Stand a Brachiosaurus in a forest and watch how it feeds. Neck extended upward, head moving slowly through the canopy, cropping needles and branches within a huge radius. No need to move the body, no need to shift 30 or 40 tons of torso and limbs every time a feeding patch is exhausted. Just sweep the neck, a gentle arc covering perhaps 100 square meters of vegetation, then take a few steps and sweep again, like a biological crane. The efficiency was extraordinary. A sauropod could spend hours feeding from a single position, extracting more calories than it spent on locomotion, while a mammalian browser of equivalent size would need to be constantly walking, burning energy just to move between food sources. Multiple lineages evolved extreme neck lengths independently. Mamenchisaurids in Asia with necks up to 15 meters long, Diplodocids in North America, Brachiosaurids on multiple continents, Titanosaurs later in the Cretaceous. Different body plans, different ecological niches, but the same solution appearing again and again because the underlying architecture made it possible. Pneumatic vertebrae, small heads, gut-based processing, the pieces fit together, and they grew fast. Bone histology reveals dense vascular channels, evidence of rapid, nearly continuous growth. Lines of arrested growth, when present, are widely spaced. The picture that emerges is of animals that went from egg to multi-ton juvenile in perhaps 10 years, then continued growing toward adult size over another decade or two. 20 to 30 years from hatching to a 30 or 50-ton adult. Absurdly fast by modern standards. A mammal that size would take decades longer to mature. Rapid growth was its own defense strategy. Predators could kill sauropod hatchlings. They could probably hunt juveniles up to a certain size. But somewhere around 5 or 10 tons, the window closed. Get big fast and you escape predation pressure before you're old enough to reproduce. This allowed sauropods to invest enormous resources in growth to push size limits in ways slower-growing mammals never could. Recent syntheses emphasize that no single factor explains sauropod gigantism. Not high oxygen levels, atmospheric oxygen in the Jurassic and Cretaceous was similar to today's, sometimes lower. Not just abundant food, other herbivores lived in the same ecosystems and didn't approach sauropod sizes. Not simply lack of predation, there were plenty of large theropods. Instead, it was the interaction of multiple traits, each reinforcing the others. Pneumatic bones made long necks possible. Long necks with small heads allowed efficient foraging. Efficient foraging supported rapid growth. Rapid growth plus gut processing plus egg-laying reproduction, lots of small offspring rather than few large ones, created a life history strategy that favoured gigantism, and the bird-like respiratory system tied it all together, allowing efficient oxygen delivery to tissues that might otherwise have suffocated under their own mass. This was a biological package, a suite of adaptations inherited from earlier archosaurs, refined by millions of years of natural selection, combined in ways that opened an ecological possibility space no other terrestrial animal lineage has ever fully occupied. Mammals evolved giant species later. Paraceratherium, 18 tons, the largest land mammal, impressive, dwarfed by even mid-sized sauropods. The pneumatic respiratory system, the egg-laying reproduction, the combination of traits, mammals never assembled the same toolkit. So when you see a mounted Giraffatitan skeleton in Berlin, or stand beneath a Patagotitan replica in the American Museum, what you're looking at isn't just size. It's the solution to a problem. How to build an animal that can weigh 50 tons and still walk, still breathe, still feed efficiently enough to fuel its own metabolism? The answer is written in every hollow vertebra, every elongated cervical, every simple tooth. It's a monument to evolutionary innovation, proof that life, given enough time and the right ancestral toolkit, can push past limits that seem absolute. But even this wasn't the end of their evolution. The Jurassic giants were only the beginning. How do you put a number on that? You stand beneath the skeleton of a mounted sauropod, neck vanishing into the rafters, tail fading away behind you, and somewhere in the back of your mind a question whispers. How heavy was this? 50 tons? 70? More? The plaques give you a neat figure, a clean number with a unit after it. But the bones themselves are silent. They don't come with a tag that says 72,000 kilograms fully loaded. And the truth is, almost none of the real giants are known the way the museum mounts suggest. Most of the biggest sauropods were not found as complete skeletons resting peacefully in the rock. They come to us as puzzles with most of the pieces missing. A handful of vertebrae from the middle of the back, a hip bone, part of a shoulder, a femur the length of a person. Sometimes that's all. The largest titanosaurs, the ones that might have pushed land animals to their absolute limits, are, in the fossil record, frustratingly incomplete. A few enormous bones, weathered and broken, hinting at living animals of unimaginable size. The rest of the body is gone, ground to sand, carried away by rivers, lost to time. So how do you weigh an animal that has been dead for 90 million years when you only have a rib and half a tail? You start with what the bones remember. One of the most powerful tools paleontologists have is hidden not in the length of a bone, but in its thickness, specifically in the girth of the weight-bearing limbs. In living four-legged animals from antelopes to elephants, there is a tight relationship between how heavy the animal is and how thick the shafts of its humerus and femur are. Not by accident. Bones grow to match the loads they carry. Too thin, and they snap. Too thick, and the body wastes precious resources. Measure the circumference of those bones in animals whose weights we can put on a scale, plot the numbers, and pattern appears. A curve that links bone thickness to body mass. Once you have that curve, you can take a fossil femur, wrap a tape measure around it, and use the same equations to estimate how heavy its owner might have been. This is limb circumference mass estimation. It's how the original mass estimate for one of our best-known giants, Dreadnoughtus shrani, was calculated. Humerus plus femur, plugged into equations derived from living animals. The answer that came out was staggering. Roughly 59 metric tons. An animal as long as a city bus, as heavy as a small herd of elephants, walking on land. But limb-bone math is only one line of evidence, and it comes with assumptions. It treats a titanosaur like just another quadruped. Bigger, yes, but built along the same engineering rules as a rhino or a hippo. Sauropods, as you've seen, were anything but ordinary quadrupeds. So paleontologists use another method, one that starts not with formulas, but with shapes. Imagine laying out all the preserved bones of a giant sauropod as they would have been in life, building a digital skeleton in 3 dimensions. You line up the vertebrae, articulate the hips and shoulders, hang the ribs in their proper arcs. It's careful work, bone by bone, angle by angle, guided by comparison with better-known relatives. Once the skeleton exists in virtual space, you wrap it, first with the simplest possible shell that still encloses every bone. A minimal shape, snug against the skeleton, like stretching plastic film around a bundle of sticks. Mathematicians call this a convex hull. Paleontologists call it a starting point. Then you expand. You add room for muscles, tendons, skin. You inflate the torso to make space for lungs and the vast fermenting gut. You allow for the air sacs that honeycomb the body. You adjust until what you have looks like a plausible living animal, not a walking skeleton or a balloon on legs. From that volume you can estimate mass depending on how dense you think the body was. Do this for Dreadnoughtus, and the picture softens. Several independent teams have used volumetric models and concluded that a more realistic mass, given the likely body proportions and all that internal air, might be closer to 30 to 40 tons. Still unimaginably heavy. Still one of the largest known land animals, but not quite the crushing 60-ton figure first proposed. Even here, with a dinosaur that preserves about 45% of its skeleton, including crucial limb bones, much of the tail and much of the torso, the uncertainty is large. 10, 20 tons of difference between methods, and that's for one of the best-known giants. But that's exactly what makes Dreadnoughtus so important. It is a reference body. A rare case where we can see most of the blueprint for a truly colossal titanosaur. Its bones tell us not just how big one individual was, but how a giant of that lineage was put together. How long the torso was compared to the tail, how high the shoulders sat, how thick the legs needed to be. When paleontologists find a lone titanosaur femur somewhere else in the world, they can compare its proportions to Dreadnoughtus and its kin, scaling up or down to get a first approximation of size. The more complete giants we have, the better our scaling gets. Another crucial anchor point in this fog of enormity is Patagotitan majorum, from the same broad region of Cretaceous Patagonia that produced Dreadnoughtus. Patagotitan is known not from a single skeleton, but from the overlapping bones of at least 6 individuals. Hips, limbs, vertebrae from different animals together give a much clearer sense of overall proportions. Reconstructing Patagotitan suggests a dinosaur perhaps 31 to 37 meters long, a body sweeping across the length of a basketball court, with a mass that most recent studies place somewhere between roughly 50 and 70 tons. Like Dreadnoughtus, the exact number depends on how robust you draw the body, how much soft tissue you allow, how much airspace you build into the model. But Patagotitan has something the true mystery giants don't. Multiple bones, many individuals, and a reasonably good idea of how its body fit together. For that reason, many researchers treat it as a top contender for largest dinosaur with solid evidence, even as they acknowledge that others may have been larger. Beyond these somewhat known colossi lie the ghosts. Names whispered in the literature and in late-night conference conversations. Brachiasaurus, described from southern India, originally known from an enormous hip element and limb bones that have since disintegrated. Amphicoelius fragilimus, now usually called Marapunisaurus, a long-necked sauropod from Jurassic North America, once reported from a single, impossibly huge vertebra that crumbled away more than a century ago. There are hints of giant Barosaurus or Supersaurus, individuals from fragmentary remains in the American West. titanosaurs from South America recorded only by their titanic femurs. In each case, paleontologists can compare the preserved piece to similar bones in better-known species and attempt to scale. But with no hips, no limbs, no neck, no overlapping bones from multiple individuals, the error bars swell. Some estimates for these ghost giants, based on the most generous interpretations, have them rivaling or even exceeding a blue whale in mass. Others, taking a more conservative line, place them only in the same ballpark as Patagotitan, Argentinosaurus, or Dreadnoughtus. With the original fossils lost or reduced to unmeasurable fragments, it may never be possible to know. This uncertainty doesn't mean the science is failing. It means we're working at the edge of what the rocks will tell us. Every method has its strengths and its blind spots. Limb circumference equations are grounded in living animals, but assume that sauropods followed the same rules. Volumetric models capture shape, posture, and pneumaticity, but depend on our choice of soft tissue thickness and density. Comparative scaling from close relatives can be powerful, but only when we are sure those relatives really are similar in proportion. So instead of asking, what did this dinosaur weigh exactly? Paleontologists increasingly ask, what is the plausible range? Maybe Patagotitan was closer to 50 tons than 70. Maybe Dreadnoughtus was still growing, a giant teenager on its way to something even larger. Maybe some fragmentary titanosaurs truly did push past every known limit, or maybe the ones we have good bones for already represent the practical upper bound of what a land animal can do under Earth's gravity. In this twilight of numbers, rankings become less important than patterns. Whether Dreadnoughtus edges out Patagotitan by a few tons, or Argentinosaurus surpasses them both, matters less than the fact that multiple lineages of sauropods converged on roughly the same colossal size range, somewhere around 50 to maybe 80 tons, 30 to 40 meters long, the edge of the possible for a creature that must carry its own weight on dry ground. When you hear different figures quoted for the same dinosaur, when one source says 50 tons and another says 35, what you're hearing are not contradictions but conversations, different ways of probing the same ancient reality, different attempts to weigh the unweighable. In the end, the mystery is part of the beauty. The bones give us shapes, proportions, clues. The equations and models give us ranges, envelopes of possibility. Within those envelopes the giants move again in our minds, heavy but graceful, step after patient step across the floodplains of the Jurassic and Cretaceous. And even as we try to measure them, they are already leading us onward. Because after Patagotitan and Dreadnoughtus, after the ghostly hints of Bruhathchaeosaurus and Marapunosaurus, the story of giant sauropods is not finished. It rises to a Cretaceous crescendo, when the last and perhaps greatest of the land-walking titans roamed a world nearing its end. By the time you reach the mid-Cretaceous, the world itself has changed shape beneath the feet of the giants. The single southern supercontinent Gondwana is tearing apart. South America pulls away from Africa, a slow-motion rift that will one day become the Atlantic Ocean. India and Madagascar begin their long journey north. Continents that once shared the same forests and river systems drift into isolation. With that isolation comes specialization. In the north, on the splintering fragments of Laurasia, the classic Jurassic sauropods begin to fade. In many places they dwindle or vanish, replaced by other herbivores. But in the south, in the breaking pieces of Gondwana, a different branch of the sauropod family steps fully into the light. The titanosaurs. They had been there already, small to medium members of a long-necked clan. But as climates shift and continents separate, titanosaurs diversify and expand. By the late Cretaceous, in South America, Africa, India, and beyond, they are no longer just part of the scenery. They are the scenery. the dominant giant plant-eaters of the southern world. And among them, in what will become Patagonia, walks one animal that may have pushed land life right up to its limits, Argentinosaurus. We do not have a complete skeleton, no perfect museum mount, just a scattering of bones discovered in the 1980s in the Winkle Formation of northern Patagonia, a series of vertebrae from the middle of the back, some ribs, a partial femur. But even those fragments are enough to bend the imagination. The dorsal vertebrae stand more than 1.5 meters tall, swollen with honeycomb chambers of air, the hallmark of sauropod bones. Ribs as thick as a person's waist arc out from the spine. The preserved piece of femur is so broad that a person can sit comfortably inside its imagined circle. Scaling from better-known relatives and using the same limb circumference equations and volumetric models that framed our view of Dreadnoughtus and Patagotitan, paleontologists arrive at cautious ranges, perhaps 30 to 35 or more meters from nose to tail, a mass somewhere in the tens of tons. Many studies cluster in the neighbourhood of 60 to 80 metric tons, with some estimates higher and others more conservative. Nobody claims to know the exact number. The bones will not say. But they do agree on one thing. Argentinosaurus was almost certainly among the largest land animals to have ever lived, a creature that pushes our models of weight, structure and biology nearly to the breaking point. To imagine such a being, you have to place it back into its world. Patagonia, about 95 million years ago. The climate is warm, seasons marked more by wet and dry than by winter and summer. Broad rivers wander across a vast floodplain, splitting into branching deltas and rejoining again, leaving behind oxbow lakes and muddy channels. On higher ground to the west, a chain of volcanic highlands smoulders. Ash drifts down from distant eruptions settling into the soil, feeding the plants that root there. Forests of Araucaria conifers rise like pillars, their whorled branches forming open, high canopies. Between their trunks grow ferns, cycads, and something new. Flowering plants, angiosperms. They began quietly in the earlier Cretaceous, small shrubs and herbs at first, but by the time of Argentinosaurus they have started to spread. Low tangles of leaves and blossoms along riverbanks, shrubby thickets bearing fruits and seeds that will one day shape entire ecosystems. The air is damp along the watercourses, heavy with the smell of resin and wet soil. Insects buzz in dense clouds over standing pools. Turtles slide from muddy banks into slow channels. Crocodile-like reptiles wait, eyes just above the surface, and then, out of the morning mist rising from a warm river, the real architects of this landscape appear, a herd of Argentinosaurus. Their steps are deliberate, unhurried. Each footfall sends a soft tremor through the saturated ground. Neck after neck, sweeping arcs of vertebrae and muscle reach forward toward the forest edge. Their heads are small for their bodies, just tools for cropping. The true machinery of feeding lies deeper, in the enormous torso where tons of plant matter will be ground and fermented by a vast gut. They move between the Araucaria trunks, stripping branches with the sideways rake of peg-like teeth. Some reach higher, stretching their necks toward the upper canopy. Others angle down, sweeping through mid-level foliage, or turn into crop at flowering shrubs along the forest margin. Together, a single herd can comb through a swath of vegetation tens of meters deep, from ground level to tree crown. The landscape is not static under such a tension. Sauropod herds like this reshape their environment, opening glades, knocking down saplings, creating patches of sunlight where flowering plants can spread. The giants and the new plants are not enemies. They are partners in a slow, reciprocal dance of eating, trampling, and regrowth. And they are not alone on their continent. Across what is now North America, near the very end of the Cretaceous, another great titanosaur roams, Alamosaurus. It lives in a different world of semi-arid plains and seasonal rivers, but its silhouette echoes that of Argentinosaurus: long neck, long tail, pillar legs. Fragmentary skeletons, including massive vertebrae and limb bones, suggest some individuals approach similar lengths and masses to the South American titans. Near Argentinosaurus-sized, some researchers cautiously say. On the other side of the opening Atlantic, along the shores of the ancient Tethys Sea, yet another giant browses a different edge. Paralititon, from what is now Egypt, lives in mangrove-fringed tidal flats. Its fossils were found among the remains of ancient coastal swamps, brackish channels, salt-tolerant trees, and mud teeming with life. Imagine a titanosaur wading belly-deep in warm, shallow water, feeding on vegetation that leans out over the tides, while fish flicker between its feet and pterosaurs glide overhead. South America holds more colossi still. Antarctosaurus, another Patagonian titanosaur, may not quite match Argentinosaurus in sheer scale, but some species seem to have been enormous in their own right, with long, low skulls and powerful bodies carrying them across the same floodplains and ash-laced soils. Titanosaurs on multiple continents, different climates, different plants, different local predators, but all converging on a similar solution: immense bodies, air-filled bones, sweeping necks, and a lifestyle built around turning plant matter into motion and muscle at a scale Earth had rarely seen on land. Why push so far into gigantism? Part of the answer may be found in the eyes watching from the shadows. In Cretaceous Patagonia, the herds of Argentinosaurus and their kin share their world with some of the largest carnivorous dinosaurs ever discovered. Giganotosaurus, a carcharodontosaurid theropod with a skull longer than a person is tall, stalks the same general regions, though perhaps not at the exact same time as every individual titanosaur species. Its relatives, like Maposaurus, are known from bone beds containing the remains of multiple individuals together. Some paleontologists look at those clustered fossils and see a hint of sociality, perhaps even group hunting, large predators working together, intentionally or opportunistically, to bring down prey far larger than themselves. Others caution that the bone beds might simply record repeated deaths at a favoured watering hole, or a herd of carnivores drawn to the same carcass over and over. The rock does not tell us their intentions, but whether they hunted in organised packs or as solitary opportunists, the effect on the herbivores would have been the same: pressure. Any juveniles or subadults small enough to tackle would be heavily preyed upon. Individuals that could grow quickly through those vulnerable sizes, or that could reach a bulk large enough to be effectively invulnerable to attack, would have an edge. Over millions of years, an arms race of size may have unfolded, predators edging larger and more powerful, herbivores responding by stretching toward ever greater heights and masses. The result, by the late Cretaceous, is a world of extremes: titanosaurs that may weigh as much as a dozen elephants, theropods whose jaws can shear through bone and muscle in a single sweeping bite, a landscape built and rebuilt by the footsteps and teeth of giants. Yet for all this might, the morning still comes softly, mist still rises from warm rivers at dawn, Araucaria crowns catch the first low light, the shadows long over the floodplain, insects hum. Somewhere, a juvenile Argentinosaurus calls to its herd, a low, resonant sound that vibrates through bone and waterlogged soil. Far off, a Giganotosaurus lifts its head, scenting the air, considering the distance between hunger and risk. None of them know that their age is finite, that the continents beneath them will continue to drift, that oceans will widen, that flowers will transform plant communities, that an asteroid still wandering far away in space is already on a collision course with their world. For now, the Titans simply are. They feed, they grow, They move in slow files across river deltas and volcanic highlands, casting shadows that stretch for tens of meters across the Cretaceous Earth. And as they do, another story is unfolding in parallel, because even while the titanosaurs rule the southern continents, other kinds of giants are taking shape in different corners of deep time. Not dinosaurs, but creatures that will follow in the empty spaces the sauropods leave behind. Creatures that will test the upper limits of land life in their own, very different ways. Not all of Earth's giants wore long necks and pillar legs. If you could drift, slowly and silently, through the Mesozoic as if it were a single long day, you would see other shapes rise out of the haze, different silhouettes on the horizon, different solutions to the puzzle of being enormous on a living, changing planet. Begin, for a moment, not with the plant-eaters, but with the hunters. On a broad Cretaceous coastal plain that will one day be western North America, the air is warm and heavy with the smell of mud and conifer resin. Low forests of evergreens and flowering shrubs fringe slow, meandering rivers. Dragonflies skim over still backwaters. Herds of horned and duck-billed dinosaurs move like living weather across the floodplain, and threading between them, keeping to the edges of the open ground, moves an animal that is huge by any ordinary standard. Tyrannosaurus rex, 13 meters from nose to tail. A head as long as a person is tall. Thigh bones thick as old tree trunks. Using the same limb bone scaling methods that help us weigh sauropods, paleontologists estimate that the largest known individuals, like the famous skeleton nicknamed Sue, may have weighed around 8 or 9 metric tons, not sauropod scale. But as a predator, that kind of mass is extraordinary. The skull is a lattice of bone, lightened by air spaces but braced like a bridge. The jaws close with a force that may have been unmatched among land animals. Teeth the size of bananas, thick and serrated, slide between bone and tendon, designed not just to slice but to crush. Each step presses deep prints into the damp ground, three-toed signatures that will one day fossilize and puzzle over future minds. Across the ancient sea, on a southern continent, another lineage of meat-eater explores its own path to gigantism. In what is now Patagonia, Giganotosaurus stalks through open woodland, roughly as long as T-Rex, perhaps 12 or 13 meters, but a little more lightly built. Estimates for its weight drift between 6 and 8 tons. Its skull is long and blade-like, teeth adapted for slashing, perhaps suited to opening great wounds in the flanks of large herbivores. Farther north and east, along the margins of Cretaceous rivers in what will become North Africa, another giant prowls the shallows, Spinosaurus. Its spine rises into a sail or hump of elongated vertebrae. Its snout is long and narrow, studded with conical teeth, more like a crocodile's than a typical theropod's. Recent discoveries suggest it spent much of its time in and around water, using a powerful paddle-like tail to swim. Limb and body reconstructions give mass estimates in the range of 7 to 9 tons, a semi-aquatic hunter comparable to the largest land predators, but adapted to a different medium, different continents, different climates, different prey. Yet all three, and several of their close relatives, converged on an upper limit for land predators, somewhere in that 6 to 9 ton range, enough weight to overpower very large victims, but light enough to walk, to turn, to chase, without the slow, ponderous constraints of the truly titanic herbivores. The plant-eaters themselves were not all sauropods either. Shift forward in time to the very end of the Cretaceous in what will become western North America. The titanosaurs have retreated from this particular stage. In their place, another caste of heavyweights dominates the greenery, ceratopsians like Triceratops. Picture a broad, low body supported on stout columnar legs. A massive skull carries 3 forward jutting horns and a great bony frill that shields the neck. Adults may have weighed 6 to 10 tons, their heads alone heavier than a small car. In herds, they move through fern meadows and angiosperm thickets, shearing plants with beak-like mouths, the scrape of horn and frill against nearby bodies a constant muted rhythm. Nearby, other giants feed on the same plains, hadrosaurs, duck-billed dinosaurs, with long, low skulls and flexible beaks adapted for cropping and grinding. In eastern Asia, on the shores of a shallow Cretaceous sea, one hadrosaur in particular pushes the limits of its lineage, Shantungosaurus. Its skeleton suggests a body 15 or more meters in length, with mass estimates commonly settling around 13 to 16 tons. A giant herbivore in its own right, roughly comparable in weight to the largest land mammals that will ever evolve, and yet still less than a third, perhaps, of a great titanosaur's mass. Armoured forms join these Cretaceous assemblies. Ankylosaurs creep through undergrowth like living tanks, their backs protected by heavy bony plates, their tails ending in dense, club-like knots of bone capable of breaking a predator's limb. Some of these armoured dinosaurs may have reached 6 or 7 tons. Short-legged, low to the ground, they traded height and reach for defence, turning their own bodies into fortresses. Together, these ornithischians, horned, billed and armoured, fill the role of large but not ultimate land giants. Big enough to shape vegetation, big enough to challenge predators, yet never quite breaching the sauropod ceiling. Above them all, literally, another lineage has stretched its own limits. Imagine standing on a late Cretaceous riverbank in what's now Texas or Romania. The sky is hazy with heat. Wind moves in slow waves through conifer crowns. For a long time, nothing larger than an insect crosses your field of view. Then a shadow passes, and the ground itself seems suddenly small. Quetzalcoatlus, Hatzegopteryx, Ajdachid pterosaurs. On the ground they stand as tall as a giraffe, perhaps 5 meters from the tips of their folded wings to their feet. Their wingspans may have reached 10 or 11 meters, some studies suggesting up to 12, though the exact numbers are still debated. Weight estimates cluster in the range of a large human to a small cow, perhaps 200 to 250 kilograms. These were not light, delicate gliders. They were robust, long-necked animals, moving on all fours when on land, using powerful forelimbs to launch themselves into the air. Once aloft, they would have cruised over coastlines and floodplains, scanning for carrion or small prey. In all of Earth's history, no other flying animal that we know of has matched their scale. While the skies host their own record holders, the seas are carrying a different kind of giant experiment. Long before the titanosaurs reached their greatest sizes, in the late Triassic oceans, sleek dolphin-like reptiles called ichthyosaurs are plying deep waters. Among them, one stands out, Shonisaurus sicaniensis. Its skeleton, discovered in what will become Western Canada, suggests a body around 21 meters long, with mass estimates that may reach 80 tons. A marine reptile roughly matching the weight of the largest sauropods, built for life in 3 dimensions, diving, cruising, perhaps surfacing in long, slow arcs. Later, during the Cretaceous, other marine reptiles take centre stage. Mosasaurs, with long, streamlined bodies and powerful tails, patrol inland seas that cut across continents. Plesiosaurs and pliosaurs, with their varying combinations of long necks or massive heads, rise and fall in the waves. Some of these marine hunters stretch well beyond 10 meters, apex predators of entire basins. Put all of this together, and a pattern begins to emerge. Across air, land, and sea, reptiles and their close relatives push body size upward again and again. Giant theropods at the top of terrestrial food webs, massive horned and duck-billed herbivores reshaping plant communities, armoured ankylosaurs turning defence into living stone, sky giant pterosaurs rewriting what is possible for powered flight, marine reptiles that grow until they rival the largest land animals ever to have walked. And yet, When you look only at animals that carried their full weight on dry land, none of these lineages ever quite catches the sauropods. Why? The answer lies partly in what you have already seen. Sauropods combined a suite of traits that together formed a kind of evolutionary key to extreme size. Air-filled bones that lightened the skeleton without sacrificing strength. Bird-like lungs that moved air efficiently through a vast body. Long necks that allowed them to stand in one place and sweep huge feeding envelopes without walking. Heads simplified into cropping tools rather than chewing machines, shifting the heavy work of digestion into a gigantic gut. Other giants touch some of these solutions, but not all. Theropods needed massive skulls and jaw muscles to hunt, concentrating weight at one end of the body. Ornithischians kept more complex chewing systems in their heads, limiting how small and light those skulls could become. Mammals later on would carry live young, nurse them, and maintain high, constant body temperatures with different respiratory and skeletal designs. Sauropods, by contrast, seem to have found a narrow, extraordinary balance point. Bodies that could grow quickly, breathe efficiently, move slowly but steadily, and turn oceans of plant matter into motion without breaking under their own mass. So when we talk about the largest creatures that ever walked the earth, the sauropods still stand alone at the very top. But they did not stride across an empty stage. They lived in a world crowded with other record seekers, other experiments at the edge of what bone and muscle and biology can sustain, and all of them, land giants and sea behemoths and sky lords alike, would eventually face their own endings. For the non-avian dinosaurs, that ending came suddenly on a single terrible day at the close of the Cretaceous, a day when the sky itself changed and the age of thunder on land came to its last dark night. The last day of the Cretaceous does not announce itself as an ending. It begins like countless days before it, somewhere on a warm, late Cretaceous coast. The air is heavy, humid, rich with the smell of flowering plants and resin. Ferns crowd the forest floor beneath towering conifers and broad-leaved magnolias. In the distance, herds of hadrosaurs move between river channels and low ridges, their calls drifting across the floodplain. Shift. Sea levels fluctuate. Some ecosystems struggle, others adapt. By the very end of the Cretaceous, life is still rich, still diverse, but there are hints of stress. Some species ranges are shrinking, others disappearing entirely. The stage, many paleontologists think, is being quietly weakened. Into this already uneasy world, something else arrives. Something from far beyond the clouds. Picture, high above the blue curve of Earth, a fragment of primordial rock, roughly 10 kilometers across, a relic left over from the formation of the solar system, wandering the inner planets on a long cold orbit. For eons it passes unremarked. Then its path intersects ours. As it hits the upper atmosphere over what will become the Yucatan Peninsula, it is moving at perhaps 20 kilometers per second. In the time it takes you to draw a breath, it has already burned through sky that would take a jet minutes to cross. Friction with the air turns its outer layers to incandescent gas. To anything alive below, it may appear first as a second sun streaking across the heavens. A moment later the rock meets shallow tropical sea. The energy released is almost beyond imagining. Estimates suggest on the order of 400 billion joules, tens of millions of times more powerful than the largest human-made nuclear explosion. In that instant, the asteroid ceases to exist as a solid object. The water above it flashes to superheated steam. The crust of the Earth behaves, briefly, like a fluid. A crater roughly 180 kilometers wide is excavated in what will one day be named Chicxulub. The immediate effects are catastrophic, but local. Shockwaves race outward at supersonic speeds, flattening forests for hundreds of kilometers. Earthquakes pulse through the crust, setting off landslides and perhaps triggering volcanic activity in regions already on edge. Ocean water piles up into walls that race away from the impact site. Tsunamis that may reach the far shores of the young Atlantic, sweeping over coastal plains where dinosaurs, pterosaurs and marine reptiles hunt and feed. But the real killing mechanism is slower, and it is global. The rock the asteroid slammed into is not ordinary stone. It is rich in sulfates and hydrocarbons, minerals and organic materials that, when vaporized, release fine dust, sulfuric particles, and soot into the atmosphere. The impact also ignites wildfires across entire continents as superheated ejecta rains down, turning forests, swamps, and plains into sheets of flame. Burned plant matter adds more carbon and blackened particles to the air. Within hours to days, the sky begins to change. Ash and aerosols spread through the stratosphere, high enough that rain cannot quickly wash them away. Dust and tiny sulfate crystals scatter and block sunlight. Estimates vary, but some models suggest that light at Earth's surface may have dropped to a pale twilight, or even near night, for weeks to months. Temperatures after a brief pulse of intense heat begin to fall. On land and in the sunlit upper ocean, photosynthesis stalls. For the great herbivores of the late Cretaceous, this is the beginning of the end. On that first night, as fires rage on distant horizons, a triceratops herd might stand uneasily under a sky streaked with falling embers. The air smells of smoke and strange, acrid chemicals. Insects fall from the air. Birds wheel and call, disoriented. Thick ash begins to drift down like a dark, warm snow, settling on leaves, on horns, on still pools of water. In the days that follow, the sunlight grows weaker. Leaves, coated with dust, cannot breathe. Some trees lose their canopies. Ferns wither along riverbanks. Pollinating insects die in swarms. The lush, green Cretaceous world begins to fade into browns and greys. Food chains do not collapse from the top. They unravel from the bottom. Phytoplankton in the oceans, unable to photosynthesize, decline. Zooplankton that feed on them suffer next. Small fish, then larger predators, feel the echo. On land, plant growth nearly stops in many regions. Herbivores exhaust stored fat and muscle as their forage disappears. Carnivores that rely on large active prey find less and less to hunt. Large bodies, which were once such powerful advantages, now become liabilities. A 10-ton triceratops needs a vast amount of plant matter to keep its warm blood moving. A 4-ton tyrannosaur requires a steady supply of meat. In a world where new plant growth has nearly ceased, the biggest animals have the least margin for error. They cannot burrow deep into the ground to wait out bad years. They cannot subsist on seeds or detritus for long. Their reproductive cycles are slow, their clutches or litters relatively small. When adults die faster than young can replace them, populations tip into decline. Smaller creatures face the same darkness, the same ash-laden rains, but some have tools that scale differently. Tiny mammals, many no larger than rats. They may have retreated into burrows, natural cracks, or dense leaf litter, insulated from the worst of the heat pulse and falling debris. Many were omnivores or insect eaters, able to switch diets as conditions changed. Seeds, roots, carrion, anything with residual energy could keep them going. Early birds, the last branch of the dinosaur family tree to survive, carried similar advantages. They were small. Many could fly to scattered refuges of remaining greenery or to coastal areas where detritus still accumulated. Some species may have relied heavily on seeds, which can persist in soils and sediments even as adult plants die. That ability, to eat preserved packets of stored sunlight when fresh leaves were gone, may have been a decisive difference. In the water, crocodilians and turtles wait in rivers and lakes. Cool-blooded, they can lower their metabolic rates, going for long periods without feeding. Freshwater systems seem to have buffered the worst effects of the impact winter. Organic debris still washes into lakes and slow rivers. Some algae manage to hang on beneath thin ice or turbid waters. In these pockets, life does not thrive, but it persists. Everywhere the same pattern repeats. Small, generalist or sheltered organisms have, on average, better odds. Large, specialized open-land animals do not. Over the next years and decades, the dust and aerosols gradually begin to settle out of the stratosphere. Rain, weak and acidic at first, scrubs the sky. Sunlight slowly intensifies again. In the wake of the fires, mineral-rich ash blankets many regions. Where seeds and spores remain viable, plants recolonize quickly. Ferns, in particular, often surge in post-disturbance landscapes. In rock layers from this time, paleobotanists see what they call a fern spike, a sudden increase in fern spores just above the thin boundary layer that marks the impact. The Earth is greening again, but it is not the same world. On most continents, the great non-avian dinosaurs are gone. Titanosaurs, hadrosaurs, ceratopsians, ankylosaurs, giant theropods. All of the animals you walked beside in your mind through the Jurassic and Cretaceous vanish from the record within a geologically brief window. Marine reptiles like mosasaurs and many large plankton-feeding animals disappear as well. Roughly 3/4 of all species on the planet do not make it through. What remains is a filtered version of the Mesozoic biosphere. Birds, the sole surviving dinosaurs, perch in recovering forests and skim over streams. Small mammals, descendants of those night-active insectivores and seed-eaters, begin to explore the newly opened niches of a world without giant reptilian herbivores and predators. Crocodilians bask along muddy banks. Turtles push slowly through weed-choked ponds. From our vantage point tens of millions of years later, the outline of this catastrophe is clear, but its details are still being traced. Some researchers argue that the Chicxulub impact was the primary trigger, a single, overwhelming blow that drove the bulk of the extinctions. Others emphasize the role of Deccan volcanism, suggesting that long-term climate swings and gradual ecological deterioration set the stage, and that the asteroid was simply the final tipping point. Still others explore the possibility that volcanic gases and impact aerosols interacted in complex ways, combining to produce a prolonged period of environmental stress. The timing of lava pulses, the exact thickness and composition of dust clouds, how long photosynthesis stayed suppressed in different regions. These questions are still being tested, revised, refined. The uncertainty is not a gap in the story, but part of its texture, a reminder that even the most dramatic events in Earth's history are reconstructed from scattered clues, layered sediments, and the chemistry of ancient minerals. What we can say, with reasonable confidence, is that on a planet that had supported land-walking giants for more than 160 million years, their last night came when the sky itself turned against them. Not with a single theatrical curtain drop, but with a spreading gloom, with dust settling over silent forests, with herds dwindling, one generation after another, until the thunder of their footsteps faded into memory held only in stone. Out of that silence, something new begins. On a young Paleogene morning, in a forest no longer overshadowed by sauropod necks or tyrannosaur skulls, a small mammal steps carefully through undergrowth. It is not large, perhaps the size of a dog or a badger, but it carries, in its bones and genes, the legacy of those that survived the impact winter. The world around it is open in a way it has not been for ages. New plants are evolving, insects buzz in different patterns. The old reptilian giants are gone. New giants will come. Not immediately, not for millions of years, but the path is opening. From here, our walk through deep time will follow them, the mammalian heirs to a world cleared by fire and shadow. We will watch, in slow motion, as bodies once again test the limits of land and air, and as Earth writes another chapter in the history of its giants. The first mammal giants do not stride onto the stage the moment the dinosaurs leave it. In the tens of thousands of years after the impact, and then in the millions that follow, the world is still catching its breath. Forests regrow, rivers carve fresh channels through sediments rich with the ashes of the old world. Birds, the last dinosaurs, fill the trees with new songs. Small mammals scurry, climb, and dig, but most of them remain what their ancestors had been for so long: modest, cautious, no larger than a modern house cat, a fox, a small dog. For a while, it is as if the planet is wary of big things. But the rules of evolution have not changed. Empty niches do not stay empty forever. The roles once filled by hadrosaurs, ceratopsians, and small sauropods are now vacant. There is sunlight to harvest, leaves to eat, seeds to crack, predators to evade, and eventually to replace. Slowly, over the long, warm interval of the early Cenozoic, mammals begin to experiment with size. In the Paleocene and Eocene, roughly 66 to 34 million years ago, some lineages start to push past the old ceiling. On broad floodplains and in dense, steamy forests, hoofed herbivores appear that are as large as deer, then cattle, then small rhinos. Their bones thicken, their limbs lengthen, their teeth change to handle new diets. Yet by dinosaur standards, these are still modest animals, the size of the smaller Cretaceous herbivores that once sculled around sauropod legs. It takes time for true giants to form, time for climates to shift, for continents to move, for new plants to challenge old bodies. By the Oligocene, around 34 million years ago, the world is no longer the greenhouse planet of the late Jurassic and Cretaceous. Global temperatures have cooled. Polar ice is beginning to form in Antarctica. Sea levels have dropped in places, exposing new land. Grasses, once minor players, are quietly spreading across open ground, changing how herbivores feed and move. Forests still stand, but in many regions they are patchier, broken by open woodland and steppe. Now, at last, something on land begins to rival the dinosaurs in sheer presence. Imagine an Oligocene dawn somewhere in Central Asia, in what is now a band of dry plateaus and deserts, stretching from Pakistan through Kazakhstan and into China. Back then, much of this region may have been open woodland and steppe. Low hills rise gently against a pale sky. The air is cool, the light thin and blue. Sparse trees, some leafed, some thorny, dot the landscape. their crowns lifted just high enough to escape the browsing of most animals. Most animals, but not all. A shadow moves along a distant ridge. At first it reads as a line of separate shapes, like a small procession of elephants seen far away. As the light strengthens, the truth resolves. It is one creature, one astonishing, slow-moving body, Paraceratherium. This animal, known from scattered but telling bones, is widely regarded as the largest land mammal to have ever lived. A relative of rhinoceroses, but without horns, it may have stood nearly 5 meters at the shoulder, taller than a 2-story building. Its head, perched at the end of a long muscular neck, could have reached 6 or 7 meters off the ground, high enough to strip leaves from trees that no other mammal could touch. Estimates vary, and paleontologists are careful to give ranges, not single numbers. The fossils are incomplete. Ribs here, limb bones there, a skull from one region, vertebrae from another, and every reconstruction involves uncertainty. But current work suggests a body length of perhaps 7 or 8 meters, and a mass in the range of 15 to maybe 20 tons. Comparable, in weight, to a mid-sized sauropod of the Jurassic, yet still only a fraction of the greatest Cretaceous titanosaurs. Under the early light, this Paraceratherium moves with deliberate calm. Each step settles with a muted thump into the dusty soil. Its skin, perhaps thick and sparsely haired, hangs in folds around the shoulders and hips. A long, prehensile upper lip or short trunk may reach for branches, curling around sprays of leaves and guiding them into a mouth equipped with heavy, grinding teeth. It is not alone. Nearby, smaller individuals move in loose association, juveniles perhaps, or other adults loosely bound in a group. Whether they lived in tight herds or more scattered bands is uncertain, but their bones turn up in the same formations, on the same ancient floodplains, suggesting that where one giant walked, others were not far away. On this Oligocene steppe, the age of reptilian thunder is long gone, but a new kind of quiet thunder has arrived, one born from mammalian lungs and hearts, from blood kept warm by constant internal heat, from muscles that never knew a dinosaur's egg. Paraceratherium is only the most extreme expression of a wider experiment. Across the Cenozoic, different mammal lineages take their turn at gigantism, each in its own way trying on the old dinosaur role of land giant, and each, in the end, finding its own limits. In Africa and Eurasia, long after Paraceratherium has vanished, another family of herbivores grows to immense size, the proboscideans, the elephant clan. Among them is Deinotherium, an elephant relative whose name means terrible beast, though its lifestyle was almost certainly peaceful. With a deep, down-curving pair of tusks on the lower jaw and a long trunk, it reached around 4 meters at the shoulder in the largest males, and perhaps 12 or 13 tons in mass, approaching the size of the biggest known elephants, but still far below sauropod scale. In South America, separated from other continents by broad oceans, evolution runs its own quiet experiments. Here, in the late Pleistocene, there appears a different kind of giant, Megatherium, the great ground sloth. On all fours, it is already massive, weighing perhaps 4 tons, as much as an Asian elephant. When it rears up on its hind limbs and balances with the help of its thick, muscular tail, it may reach 6 meters in height. Huge claws curl from its forelimbs, not for hunting, but likely for pulling down branches or defending itself from predators bold enough to approach. Slow, heavy, wrapped in a thick hide and perhaps a shag of fur, Megatherium turns the sloth's usual association with smallness and treetops inside out. It is a browser on the ground, a forest of muscle and bone that can reach into the crowns of trees. Farther north and west across the Eurasian plains, another giant grazer roams, Elasmotherium, sometimes called the giant rhinoceros. It is not as large as Paraceratherium, Estimates place it around 3 to 5 tons, 2 meters or more at the shoulder, perhaps 4.5 or 5 meters in length. But in its own time it must have been impressive. Some reconstructions give it a hugely thickened nasal region, suggesting support for a large horn. Others urge caution, pointing out that the exact size and shape of that horn are speculative. What is clear is that Elasmotherium was a powerful, heavy-bodied animal, adapted to open grasslands and cold steppe climates as the ice ages drew near. All of these mammals are giants by our standards, by Ice Age standards, even by most Mesozoic standards. But none of them approach the heavier sauropods. Not Paraceratherium, not Dinotherium, not the largest elephants or ground sloths. There seems to be a ceiling on how big a warm-blooded, chewing, live-bearing mammal can become while still walking on land. Why? Part of the answer lies inside the chest. Sauropod dinosaurs, like modern birds, probably had a flow-through lung system linked to air sacs that extended into their bones. This arrangement is remarkably efficient. Fresh air passes in a loop, old air is cleared more completely, and the system doubles as a way to lighten the skeleton. Many sauropod bones are honeycombed with air spaces, reducing weight without sacrificing strength. Mammals breathe differently. Our lungs and those of our giant relatives work on what biologists call a tidal system. Air moves in and out of the same sacs, mixing fresh and stale each breath. It works well enough for animals up to elephant size and beyond, but it is less efficient at scaling to truly enormous bodies that need to move oxygen through thick muscles and up long necks. Our bones are also more uniformly dense, lacking the extensive air-filled cavities of sauropods, which means that, kilogram for kilogram, a mammal skeleton tends to be heavier. Then there is the matter of food. Sauropods, with their small heads and simple teeth, seem to have adopted a swallow now, process later strategy. They could crop huge volumes of relatively low-quality plant material and let enormous guts and long digestive tracts do the work. Mammals, by contrast, generally chew. We have complex teeth, intricate jaw joints, and thick layers of muscle to grind food before it reaches the stomach. In giant mammals, that means carrying a heavy skull and massive jaw muscles at the end of the neck, where leverage is least efficient. Every extra kilogram of head and jaw is a cost that must be paid in thicker necks, stronger shoulders, sturdier limbs. Reproduction sets another bound. Sauropods, like other dinosaurs, laid eggs. A large female could, in principle, lay many eggs over a season, spreading her reproductive risk and allowing populations to rebound more quickly after losses. Mammals, especially large ones, invest heavily in a small number of live-born young. Gestation is long, childhood is extended. An elephant or rhino may rear only a handful of calves in a lifetime. A giant mammal lineage cannot bounce back as quickly from droughts, diseases, or the arrival of efficient new predators. The larger the body, the slower the turnover, and the more vulnerable the species becomes to sudden change. These are not hard, absolute barriers, but they are strong tendencies. Layered on top of them is the changing stage of the Cenozoic itself. As the ages advance from Paleocene warmth through Oligocene cooling into the wild swings of the Pleistocene ice ages, climates become more variable. Ice sheets grow and shrink, sea levels fall and rise. Grasslands spread, favouring herbivores that can run and graze across open expanses rather than stand, sauropod-like, in one place stripping trees. Under such conditions, being moderately large and fast may be more consistently rewarded than pushing body mass into the 50 or 70-ton realm. And so mammalian giants stay within their band. 10 tons, 15 at the outside according to current estimates. Impressive, powerful, world-shaping in their own right, yet always smaller than the greatest reptiles that came before. On that Oligocene steppe, as the Paraceratherium you imagined finishes feeding and turns slowly toward distant hills, the sun has now cleared the horizon. Its light spills across grasses and low shrubs that would look vaguely familiar to you in a sky almost the same blue you know. Birds flit between trees, small mammals rustle in the undergrowth, ancestral horses, three-toed and slender, move at a cautious trot near the horizon. It is a world both alien and recognizable. The continents are drifting into arrangements you would recognize on a modern map. Mountain ranges are rising that you could hike today. Temperatures are cooler than the Jurassic, seasons sharper, the air perhaps less heavy, the nights colder. The thunder of the old giants is gone, but the Earth has found new ways to test the limits of size. These experiments in mammalian gigantism will not last forever. Climate will continue to cool. Ice will advance and retreat. Some giants will vanish quietly, others may fade in the shadow of a new, clever predator that walks on two legs and carries tools made of stone. But before we reach that edge of memory, the planet will host one more cast of enormous land animals. The Ice Age megafauna, whose bones still lie within arm's reach of human history. To meet them, we follow time forward again, into colder winds, longer winters, and plains crossed by mammoths, mastodons, and other giants standing at the very brink of our own story. Glaciers advance from the north, carving valleys, grinding mountains to flour, locking up so much water that sea levels fall and expose new shelves of land. Then, over thousands of years, the ice retreats. Forests creep back, lakes swell and overflow. Then the cycle begins again. Over and over, for more than 2 million years, the planet breathes in ice and exhales warmth. This is the Pleistocene, the last ice age. Not one long frozen night, but a pulse of glacial and interglacial periods, each reshaping the map of climates and habitats. In these shifting conditions, new giants appear, creatures enormous by any standard, yet close enough to our own time that their memory almost reaches us. Across the northern half of the world, from Europe to Siberia to North America, an extraordinary ecosystem spreads during the colder phases. Paleontologists sometimes call it the Mammoth Steppe, a vast, mostly treeless grassland stretching from Ireland almost to Alaska, bound together by wind and cold and short, intense summers. Here, under low winter suns and long twilight skies, the ground is hard, the air dry, the vegetation tough and close to the soil. Moving across this landscape are the most familiar of the Ice Age giants. Mammoths. Picture a family of woolly mammoths, Mammuthus primigenius, cresting a low rise in that endless grassland. The adults stand perhaps 3 to 3.5 meters at the shoulder, as tall as a large modern elephant weighing 6 to maybe 8 tons. Their silhouettes are high-domed, their backs sloping down toward short, powerful hindquarters. Long, spiraling tusks curve forward and up, tracing pale arcs against the grey horizon. Every part of their bodies is built for cold. Thick fur with a shaggy outer coat and a dense underwool beneath. Fat 8 centimeters thick beneath the skin, insulating organs and muscles from the brutal air. Small ears and short tails to minimize heat loss. Even their blood may have carried molecular tweaks that helped oxygen flow easily at low temperatures. They are, in their way, as specialized for this climate as sauropods were for Jurassic warmth. To the south and west, in more temperate regions of North America, another kind of giant elephant relative roams the plains and open woodlands, the Columbian mammoth, Mammuthus columbi. Less furry than its northern cousin, more suited to milder winters, it may stand close to 4 meters at the shoulder and weigh perhaps 10 tons in the largest males. If you stood at its shoulder, your head might barely clear its elbow. It walks through mixed grass and scrub, crossing rivers and open savanna, its trunk sampling the air for scent, its tusks sweeping low over the ground. Sharing these continents with the mammoths is a different lineage of proboscideans altogether, the mastodons. Mammut americanum, the American mastodon, is shorter and more heavily built than a typical mammoth, 2.5 to 3 meters tall, perhaps 4 or 5 tons in mass. Its teeth tell a separate story, where mammoth molars are flat-topped and ridged, made for grinding grasses and sedges. Mastodon molars are studded with conical cusps, better suited to chewing twigs, leaves, and branches. Instead of the open mammoth steppe, mastodons prefer forests and wetlands, browsing among conifers and hardwoods, their footprints sinking into soft leaf-littered soil. The Ice Age does not keep its giants confined to the north. In South America, the great ground sloth Megatherium, which we met on its own terms a moment ago, is now joined by a whole menagerie of large herbivores and predators, each adjusted to the new beat of glacial cycles. The largest Megatherium individuals, 3 or 4 tons in mass and up to 6 meters from nose to tail, still rear to strip foliage from trees, but around them graze glyptodonts, armoured mammals the size of small cars, and herds of robust camelids and horses that reach the continent in waves when land bridges opened. Far away, on the isolated stage of Australia, evolution writes a different chapter. Here there are no native mammoths or mastodons, no rhinos or giant ground sloths. Instead, marsupials take on the giant role. Among them, one stands out, Diprotodon optatum. Diprotodon is often described a little loosely as a giant wombat. It is not a wombat in the strict sense, but it is a close relative, and the comparison captures something essential. Imagine an animal 3 meters long, 2 meters high at the shoulder, weighing perhaps 2.5 or nearly 3 tons. Its skull is large and blunt, with 2 prominent lower incisors and a jaw built for grinding tough, dry vegetation. It plods across Australian plains and woodlands from about 1.6 million years ago to as recently as 40 or so thousand years ago, browsing shrubs and low trees, visiting lakes and waterholes that would one day become dusty basins and salt pans. The largest marsupial ever known, it presses marsupial biology to the same kinds of limits that mammoths press placental biology elsewhere. In the colder parts of Eurasia, other Ice Age giants prowl the edges of the mammoth steppe. One of the most imposing is the giant short-faced bear, Arctodus simus in North America, and its close relatives in the Old World. Reconstructions suggest that the largest individuals may have weighed as much as modern polar bears or more, possibly approaching a ton, and when they reared up, they could have towered over any human who might have seen them. Their long legs and broad chests hint at powerful, fast movement over open ground. Whether they were primarily hunters, scavengers, or a mix remains debated, but in either case, they were top-level carnivores, shadows at the edge of every herbivore's awareness. Alongside them move the cave lions, Panthera spelaea, larger than modern African lions, some males perhaps nearly as tall at the shoulder as a small human child. Their bones gather in caves across Europe and Asia, sometimes with faint ochre outlines and scratched lines on the rock walls nearby. Later humans, survival partners and competitors of these lions, will leave images of them staring out from the dark, and above some of these scenes, in cool, open woodlands and along the margins of bogs and lakes, strides a deer that looks as if it stepped from mythology, the Irish elk, Megaloceros giganteus. Despite its common name, it is not especially close to modern elk. It is its own grand experiment in antler size. A large male Irish elk stands nearly 2 meters at the shoulder, its body mass similar to or exceeding that of a modern moose. But what you notice first and cannot look away from are the antlers, a spreading crown of bone that can span 3.5 meters from tip to tip and weigh 40 kilograms or more. Each autumn this weight grows from living tissue, fueled by rich summer forage and surging hormones. Each winter or early spring it is shed and lost, only to be grown again when the days lengthen. In that rhythmic building and discarding of vast antlers, you can feel the Pleistocene's own cycles mirrored on a smaller living scale. For hundreds of thousands of years, this Ice Age world of giants is stable in its instability. Ice advances, giants track the shifting lines of grassland and forest. Predators follow. Extinctions occur, but they are scattered, local, part of the background rhythm of evolution. Then, near the very end of the Pleistocene, something different happens. The ice retreats for the last time. From about 20,000 years ago onward, the great northern ice sheets begin a final sustained withdrawal. Temperatures rise, sometimes abruptly on human timescales. The mammoth steppe shrinks. Grasses that once covered entire continents give way to expanding forests, wetlands, and, in some regions, tundra. Habitats that supported enormous herds of cold-adapted grazers fragment into patches, then islands, then vanish altogether. At almost the same moment, another change spreads across the maps. Modern humans, Homo sapiens, already present in Africa and parts of Eurasia, begin to appear in region after region that had not known them before. Australia, by around 65 to perhaps 50,000 years ago, Europe earlier still, Siberia, and then the Bering Land Bridge, the Americas by at least 15,000 years ago and likely somewhat earlier, the exact timing still under active study. Wherever humans arrive, bones and stone tools begin to mingle. This double pressure, rapid climate warming, and the spread of a new, highly adaptable predator forms the core of one of paleontology's most enduring debates. Why did the Ice Age giants vanish? Some researchers emphasize human hunting. They note that on many continents, waves of megafaunal extinction seem to follow closely after the first secure signs of human presence. In Australia, many large marsupials, including Diprotodon, disappear not long after modern humans arrive. In the Americas, mammoths, mastodons, giant ground sloths, and others decline sharply in the window after people cross from Siberia. Stone spear points and butcher marks on bones show that humans were not just passive observers. They hunted, scavenged, and learned quickly which large animals were easiest to approach and bring down. Others point to the climate itself. The end of the last glacial period was not a smooth, gentle climb toward modern conditions. It was punctuated by abrupt swings, cold snaps like the Younger Dryas, rapid bursts of warming, shifts in rainfall patterns. The ecosystems that had sustained mammoths and their companions were tuned to cold, dry, stable conditions. As warmth and moisture returned, forests expanded, wetlands spread, and the open, windy grasslands that once stretched from horizon to horizon broke apart. Even without humans, some populations of large, cold-adapted herbivores may have been in trouble. Many paleontologists now suspect that the truth is not a simple either-or, but a combination. Climate change may have shrunk and fragmented habitats, reducing population sizes and making megafauna more vulnerable. Human hunting, even at relatively modest rates, could then have pushed these already stressed populations past the point of recovery. On some continents, climate might have been the main driver, with people as a secondary pressure. On others, especially where human arrival was sudden and climate had already begun to shift, hunting and perhaps human-set fires may have played the larger role. The balance likely varied from place to place. What remains, as the Pleistocene fades into the Holocene around 11,700 years ago, is a quieter world. The last woolly mammoths on the mainland Eurasian steppe vanish. Small, isolated populations linger for a time on Arctic islands. Like Wrangel, their bones recording a final echo of a way of life that once ruled half the globe. In North America, mastodons and mammoths and giant ground sloths fall silent. In Australia, Diprotodon and many of its megafaunal neighbours are gone. The Irish elk persists in some regions until only a few thousand years ago, then disappears as well, its great antlers becoming curiosities washed from ancient bogs. We live in the aftermath of that thinning. Today's elephants, bison, moose and rhinos are the last representatives of a broader, richer tradition of large land animals. Compared to the Jurassic, compared even to the mid-Pleistocene, our world is a world of smaller giants. And yet, even as the land lets go of its largest forms, another realm is quietly pushing body size further than any sauropod ever did. While mammoths walked their final paths along frozen rivers, in the oceans around them something else was growing, feeding, and learning to use the buoyancy of seawater to sidestep the limits that had constrained land giants for so long. To meet those leviathans, we have to leave the mammoth steppe behind, follow the retreating glaciers down to the coasts, and step off the continental shelves into deep, dark water where the largest animals of all time still swim. Behind you lie the tracks of mammoths, mastodons, and giant deer. Ahead of you, the continent drops away. The air smells of salt and cold, and the sea rolls in long heavy swells dark under a low sky. Beneath those swells waits a different kind of giant. Imagine sinking gently through the surface, the roar of the surf fading to a muffled hush. Light filters down in shifting bands. The cold presses in, then eases as your body adjusts. Around you, the water is not empty. Tiny particles drift and glint. Plankton, the foundation of almost everything that lives here. Far below, you feel more than you see it at first, a presence passing under you, like a moving shadow the size of a city bus, then longer than any bus, then longer than a train of buses end to end, a shape as long as a basketball court followed by another half a court. 30 meters of living animal, a mass that might reach 150, even nearing 200 metric tons in the largest individuals. This is a blue whale. Sauropods once walked the earth in herds, their necks towering over forests. Some of them may have reached 30 or more meters in length, and the most massive probably weighed 50 to perhaps 80 tons, maybe a bit more in the most speculative reconstructions. Enormous by any terrestrial standard. Yet here, gliding through the dim water, is a creature not only comparable in length, but decisively heavier. By mass, by the simple measure of how much matter is bound into a single metabolism, the blue whale is widely regarded as the largest animal known to have ever lived. And it is alive now, somewhere in the oceans of our present Earth, breathing. To understand why the ocean still harbours such giants when the land has long since let go of them, you have to think like physics and evolution at the same time. On land, gravity is always pulling you down toward a hard, unyielding surface. The bigger you get, the worse the engineering problem becomes. Double an animal's height, and its weight more than doubles. The stresses on bones and joints rise faster than their strength. A sauropod's massive columnar limbs are evolutionary compromises with this relentless arithmetic. Its skeleton is both strong and ingeniously lightened with air spaces, its posture tuned to distribute forces across pillars of bone. In water, the rules change. Seawater is dense, it pushes back. A body that would crush its own legs on land is buoyed up here, supported from all sides. Gravity still acts, but its bite is softened. You do not need columns of bone thicker than a human torso to hold yourself up. You do not need to worry about your own weight, grinding your joints to dust each time you take a step. This buoyancy is the ocean's first gift to giants. It relaxes the structural limits that capped body size on land. A whale skeleton can be relatively gracile compared to a dinosaur of similar length, because it is never truly bearing its full weight on a point or a limb. Its body can expand outward, thickening with muscle and blubber without the same catastrophic consequences that expansion would have on a savanna. The second gift is temperature. Water steals heat faster than air. For small animals in cold seas, this is a constant danger. But for large animals, it becomes an opportunity. The bigger you are, the smaller your surface area is compared to your volume. Heat generated in your core leaks away more slowly. A huge body becomes a thermal fortress, able to cruise through polar and subpolar waters without freezing. A thick layer of blubber stores energy and insulates. Muscles can run at a steady, efficient temperature even in near-freezing seas. In such an environment, gigantism is not just possible, it is useful. It stabilizes your internal world against the fluctuations of the external one. But buoyancy and heat alone do not build a blue whale. They only make it possible. To actually sustain 150 tons of living tissue, you need food, immense amounts of food, delivered in a way that makes sense energetically. A giant that must chase down individual, fast-moving prey will spend more than it gains. The ocean's third gift is that it sometimes concentrates its life into rich, dense patches. In high latitude and upwelling regions, cold, nutrient-rich water rises from the depths. Sunlight fuels explosive blooms of phytoplankton near the surface. Tiny crustaceans, including krill, graze on this invisible pasturage, and under the right conditions they gather themselves into swarms, clouds of life that can stretch for kilometers, millions upon millions of small bodies layered in the water like drifting living dust. To a giant filter feeder, these swarms are the equivalent of an endless field of grain. Blue whales and their close relatives, the rorquals, have evolved to harvest them with almost outrageous efficiency. They accelerate toward a krill patch, open their vast mouths, and engulf a volume of water larger than their entire body. Pleated throat grooves expand like an accordion. Then the jaws close, the tongue and muscles press the water out through curtains of baleen, and a concentrated slurry of krill slides down the throat. A single good lunge can yield tens of kilograms of food. A successful day's feeding may take in several tons. For an animal this large, there is no other strategy that works as well. Do not pick, do not chase. Sweep the ocean itself into your mouth and let the baleen sort it. And here, evolution plays another quiet trick. Evidence from fossils and from models of ancient oceans suggests that the very largest rorquals did not arise in some primordial Mesozoic sea. They appear relatively late. Many researchers argue that truly enormous blue and fin whales only evolved in the last few million years, deep in the same ice age whose aftermath we have just walked through on land. As the Pleistocene glaciers advanced and retreated, they changed not only the outlines of the continents, but the patterns of wind and current. Stronger, more seasonal upwelling along certain coasts may have turned stretches of ocean into periodic buffets, where productivity surged in brief, intense pulses. In such seas, food is not spread evenly, but gathered into feast or famine patches. Under those conditions, being big, fast-moving, and able to gorge on massive swarms within a short feeding season becomes a winning strategy. Natural selection may have ratcheted baleen whales upward in size, generation after generation, until they reach the prodigies we know today. Blue whales are not alone in this marine gigantism. Close relatives, fin whales, can reach over 20 meters and perhaps 70 or 80 tons. Sperm whales, with their blocky heads and deep diving habits, are smaller in mass but still immense. Males up to 20 meters long and around 50 tons, yet they are not filter feeders. They are hunters, the largest toothed predators known, plunging a kilometer or more into the dark to find squid in the black layers of the midwater realm. Other giants share the sea in different roles. The whale shark, a fish, cruises warm tropical waters with a mouth like a gentle cave, filtering plankton and small fishes through gill rakers, growing to 18 meters or more. Deep in the mesopelagic zone, giant oarfish undulate like living ribbons of silver, their long, narrow bodies stretching 8, 10, perhaps 11 meters, yet weighing far less than their length would suggest, delicately built for a life of slow motion in thin twilight water. Even when we look back into the age of reptiles, into Mesozoic oceans filled with ichthyosaurs, plesiosaurs and mosasaurs, the balance of size remains striking. The largest known shastosaurid ichthyosaurs, like Shonisaurus and its kin, may have approached 20 or perhaps 25 meters in length. The biggest mosasaurs were formidable predators, their bodies as long as a bus, their jaws lined with teeth. Yet by current estimates, even these marine reptiles were probably lighter than the heaviest blue whales. Marine gigantism has not simply been a Mesozoic story carried forward. It has its own crest and timing, with its highest wave rising in the very recent past. All of this leads to a quiet, almost unsettling thought. Across 4.5 billion years of planetary history, through all the experiments of trilobites and ammonites, armoured fish and soaring pterosaurs, swamp forest amphibians and thunder-footed sauropods, the largest animal we know of is breathing air somewhere above a deep trench right now, its heart beating slowly beneath a rib cage the size of a small room. We live at the same time as that animal. Our ships share the surface of its world. Our noise echoes through the water it uses to communicate. Our nets and lines and changing climate tug at the web of life that feeds it. Like the mammoths at the end of the Ice Age, blue whales and their kin exist at a point of tension. They are survivors of the most intense whaling campaigns in human history. Their numbers cut to a fraction of what they may once have been. They face ship strikes, entanglement in fishing gear, and the slow rearrangement of ocean currents and plankton blooms as the climate warms. Their future is not guaranteed, and so, when you picture a blue whale easing its immense body through the dim blue light, each exhalation sending a column of spray into the air above, you're not looking back into a lost world. You're looking at a living edge of possibility, at the far end of a spectrum of size that Earth's physics and biology have allowed exactly once, so far as we can tell. The land has given up its largest forms, the seas still cradle theirs. But even the ocean has limits, and even its greatest leviathans are not beyond the reach of change. To understand what those limits are, and why nothing even larger may ever walk the earth again, we have to leave the whales in their dark rolling kingdom and turn back toward the shore, toward gravity, bone, and the quiet arithmetic that governs every giant's rise and fall. On land, every giant lives at the mercy of a simple rule. As a body grows, its length, width, and height might double. But its mass does more than that. It climbs with the cube of size. 2 times taller becomes 8 times heavier. The cross-section of a bone, the area of a joint surface, the place where muscles anchor, all of that only grows with the square. Biologists call this the square-cube law. Evolution never named it, but evolution has been obeying it for hundreds of millions of years. You can walk through the logic slowly. Picture a small lizard scurrying across a rock. Its bones are thin, its muscles wiry. Now imagine scaling that animal up, keeping all proportions the same, until it weighs 50 tons. The weight pressing down on each limb has risen far faster than the strength of the limb itself. Every step becomes a risk. Joints are squeezed, bones bent, tendons loaded until sooner or later something gives. Sauropods did not simply ignore this law. They bent their entire anatomy around it. Their limbs shifted from the sprawled posture of their reptile ancestors to straight, vertical columns. The upper arm and thigh bones became massive, the lower segments stout and pillar-like. The joints lost some flexibility and gained stability, the way a building trades mobility for strength. With each step, forces travelled straight down through the limb into the ground, minimizing bending and twisting that would have snapped a lighter frame. Their vertebrae became airy cathedrals of bone, laced with internal struts and filled with air sacs. Their tails served as counters and braces. Their long necks, for all their apparent delicacy, were supported by a complex system of ligaments and pneumatic chambers that reduced weight where it mattered most. Even so, there are signs that they approach the edge of what bone can bear. Analyses of their limb bones suggest safety margins thinner than those of most modern mammals. They lived close to the red line, but not past it. 50, 60, perhaps 70 tons in the largest well-known species, Patagotitan argentinosaurus dreadnoughtus. Enough to dwarf an elephant several times over, perhaps enough to brush against the absolute mechanical limits of a walking animal. If anything larger ever tried to walk, it would need bones thicker still, joints broader, muscles larger. But remember the square cube law. Those thicker bones would themselves add mass. The animal would weigh more not only because it was bigger, but because the scaffolding needed to hold it up had grown heavier. Each improvement calls forth a new problem. Each solution moves the limit a little, but the curve always rises faster than the fix. There is another quiet arithmetic at work too. Heat. Inside every large body, cells burn fuel. That burning produces energy and warmth. As bodies grow larger, their internal volume, the source of heat, rises faster than their surface area, the place where that heat can escape. A mouse loses warmth almost as soon as it makes it. An elephant holds on to it. A giant holds on to it even more. For a creature the size of a sauropod, overheating may have been as dangerous as breaking a leg. Too much muscular activity under a hot sun, and the internal temperature could creep upward into lethal ranges. Some studies suggest that sauropods ran cooler than modern mammals, with body temperatures closer to those of big reptiles, using their sheer mass to keep things stable, what researchers sometimes call gigantothermy. Others argue they were more warm-blooded with higher metabolic rates. Whatever the exact numbers, there is broad agreement that shedding excess heat would have been a constant challenge. Here, again, their anatomy hints at solutions. Air sacs woven through their bones connected to lungs thought to have been bird-like, a one-way flow system, more efficient at moving air than the bellows of a mammal chest. This same network that lightened their skeleton may have acted as an internal radiator, flushing heat away from working muscles into the vast volume of air passing through the body. Their muscles, relative to their size, may also have been modest. When you look at a sauropod skeleton, you do not see giant flaring crests and ridges for enormous limb muscles the way you do in some theropods. They did not sprint. They did not leap. They walked, slowly, steadily, piston-like. Less explosive muscle means less sudden heat. Even with all this, there are limits. Make an animal larger still, and its surface area shrinks further in proportion to its volume. Its ability to vent heat drops. Unless you cool the climate dramatically, or slow the metabolism to a crawl, the giant cooks itself from the inside out. Then there is the question of food. A 70-ton herbivore is not sustained by a patch of shrubs. It is not even sustained by a single forest. It needs landscapes, rolling, continuous expanses of productive vegetation, renewing themselves quickly enough that today's meal does not starve tomorrow's. Models of sauropod ecology suggest that they may have spent most of their waking hours feeding, gathering tens or hundreds of kilograms of plant matter each day. Their long necks increase the radius of each step's reach, letting them harvest a wide swath of foliage without moving their massive bodies as often. Their swallow-don't-chew strategy shifted the work of processing plants from the mouth to the gut, allowing smaller heads at the ends of long necks. All of this made extreme size more efficient. A bigger body can carry a bigger digestive factory. A bigger gut can extract more from tough, low-quality plants. But there is a threshold where the landscape itself becomes the constraint. If the vegetation can't regrow fast enough, if the habitat is broken up by barriers, if migration corridors are cut, A giant starves long before it reaches the age its genes are aiming for. In the Mesozoic, especially in the Jurassic and parts of the Cretaceous, many regions seem to have offered such continuous lush environments. Warm climates, high plant productivity, vast floodplains and open woodlands. Some researchers once pointed to higher oxygen or carbon dioxide levels as the main key to dinosaur gigantism, imagining a world where air itself encouraged giants. But as atmospheric reconstructions have improved, a more subtle picture has emerged. Oxygen levels through the Mesozoic appear to have fluctuated, sometimes above, sometimes below modern values. Carbon dioxide was often higher, yes, but that does not automatically translate into supercharged ecosystems. The consensus among many paleontologists now is that, while global climate and plant communities set the stage, the real drivers of sauropod size were their own biological tricks. The air sac systems, the lightened bones, the egg-laying strategy that allowed many offspring, the rapid growth, the long-necked foraging, the simplified chewing. Together, these formed a kind of evolutionary toolkit that no living land lineage quite matches. Large mammals carry heavy, solid bones and give birth to a few well-developed young after long pregnancies. Their lungs are efficient but lack the continuous flow design of birds and, by extension, sauropods. Their teeth and jaws are committed to heavy chewing. They are powerful, but they are also constrained in different ways. Could we, with all our technology, ever bring giants like the old ones back? People sometimes imagine resurrecting dinosaurs through de-extinction, or even engineering new colossi from scratch. It is an intriguing idea to roll around in the mind at night. A modern savanna with a herd of recreated titanosaurs moving across it, their silhouettes backlit by a familiar sun. But when biologists look closely, the obstacles multiply. The genomes of non-avian dinosaurs are gone. Their closest living relatives, birds and crocodilians, cannot simply be scaled up to 60 tons by changing a few genes. The intricate architecture of pneumatic bones, the specific pattern of air sacs, the reproductive strategy of laying massive clutches of eggs in secure environments, the growth programs that turned a hatchling into a 30-meter adult in a few decades. These are not single traits, but whole networks. Even if, in some hypothetical future, we could approximate such a creature, the wider world it would need is no longer waiting. Modern continents are sliced by roads and cities, fenced and ploughed, their forests converted to patchwork. The kind of contiguous habitat that once supported herds of sauropods or legions of mammoths is rare and shrinking. Climate is changing quickly. Pressures from humans press in from every side. An engineered giant might stagger a few steps into such a world, but it would be walking into an ecological maze built for smaller, more agile forms. So when we say the age of terrestrial giants may be over, we are not claiming that life has lost its inventiveness. Evolution continues to explore, to improvise, but the particular combination that built Argentinosaurus and its kin, the physics of bone, the physiology of air sacs, the climate and plants of the Mesozoic, the absence of certain competitors and the presence of others, was a moment. Long on our scale, brief on the planet's. Moments in deep time do not repeat exactly. Continents move, atmospheres change. Once a pathway closes, evolution does not simply turn around and walk it again. It moves on, trying new directions. We live in one of those new directions now. Our giants are whales in the sea, elephants on land, redwoods and sequoias lifting their bulk in place instead of in motion. They are immense, but they are not what walked here before. Somewhere a blue whale rises, exhales, and sinks again. Somewhere else an elephant shifts its weight and settles to sleep. Under their skin, in their bones, the square-cubed law still whispers its constraints. Heat still builds and must be lost. Food still must be found. Limits still exist. The dinosaurs didn't fail because they reached those limits. They touched them, used them, and for tens of millions of years lived within them as well as any animals ever have. When their time ended, it was not the square cube law that struck them down, but rock from the sky and fire from within the earth. Yet the quiet arithmetic they wrestled with remains, shaping what may yet evolve and what will never quite be again. From here, from the thin layer of the present, you can look back along the trail of footprints, sauropods and titanothers, mammoths and whales, each giant a different answer to the same hard questions of gravity and heat and hunger, and beyond them, further still, away from flesh and bone altogether, there are the older records, the ones written not in living tissue, but in stone. Those older records are where our walk began. In the dim aftermath of the Permian, when most complex life had already gone silent, we stepped out onto scorched floodplains, where the first hesitant forests were reclaiming a wounded world. The land was poor and open, the air heavy with ash and dust. Early Archosaur relatives moved with careful steps across mud that still remembered the great dying. From there, we followed the clock forward. We watched Archosaurs rise from obscurity to dominance, shouldering aside other reptile lineages. We saw the first long-necked experimenters appear, modest compared to what was coming, but already hinting at a new way to be alive on land. Big bodies, columnar limbs, a diet drawn from the high canopy. We walked into Jurassic floodplains, warm and humid, where conifer forests fringed broad rivers and ferns carpeted every open patch. Herds of sauropods, some of them already approaching 20 or 30 meters in length, moved like living hills through morning mist. Each step shook the ground, each tail sweep folded air. Thunderstorms gathered in the afternoons, and the thunder on the horizon answered the quieter thunder underfoot. We traced the path into the Cretaceous, where continents drifted and climates shifted. Flowering plants spread along river deltas and coastal plains, changing the menu for giant herbivores. Titanosaurs like Argentinosaurus and Patagoteton, perhaps 50 to 70 tons in the largest individuals, pushed body size to new extremes. Evidence suggests some of them browsed in open woodlands crossed by braided rivers, their necks sweeping over stands of early flowering trees, their eggs buried in sandy nesting grounds under a hotter sun. We watched that chapter close. Around 66 million years ago, a rock from space, maybe 10 or 15 kilometers across, fell into what is now the Yucatan Peninsula. It carved the Chicxulub crater into the crust and threw vaporized rock and dust high into the sky. A thin layer rich in iridium, metal from beyond Earth, settled out over the entire planet. Forests burned, skies darkened, food chains faltered. Non-avian dinosaurs, including the last sauropods, vanished. So did many flying reptiles, marine reptiles, ammonites, and countless smaller, quieter forms whose names we will never know. Perhaps 75 or 80% of species disappeared in that single jagged boundary in the rock. And yet, even there, the story did not end. Within thousands to hundreds of thousands of years, burrowing animals were reworking the seafloor. New plankton lineages were seeding the oceans. On land, small mammals, turtles, crocodilians, and the surviving birds, tiny descendants of theropod hunters, began filling the empty spaces. The titans had fallen, but life itself had not. We followed these new giants as they appeared. Paraceratherium, the towering Oligocene mammal that may have browsed over treetops in ancient Asian forests. Ice Age mammoths and ground sloths, living through long winters and short summers on wind-swept steppe. Then further still, to the present, where the largest creatures of all time glide not across land, but through water. Blue whales, perhaps 100, maybe 180 tons in the biggest estimates, drifting through cold oceans made dense and supportive by salt and depth. Heavier than any sauropod we know, but bound to the sea that holds their weight. Taken together, all of these giants whisper the same lessons. They remind us that dominance is temporary. Sauropods ruled terrestrial size classes for tens of millions of years. Many dinosaur groups seem to have been thriving right up to the impact, not fading gently away. Yet a single, unlucky alignment of rock and orbit erased them as thoroughly as the smallest insect. They show us how inventive evolution can be. Long necks, air-filled vertebrae, efficient bird-like lungs in sauropods, trunk and tusks in mammoths, baleen plates in whales. Each lineage found its own path to bigness, its own compromise with gravity, heat, and hunger. At the same time, they reveal how fragile the conditions for extraordinary life can be. A shift in climate, a rearrangement of continents, a change in plant communities, an asteroid strike. Any of these can close the narrow window that allows a 50-ton animal to walk or a 100-ton animal to swim. And now, here we are, on the thin, warm surface of the present, able to read those stories in stone. If this slow journey through deep time has kept you company tonight, you might, if you feel like it, let the world know. A gentle tap on the like button helps more wandering minds find their way here. If you'd like to share a small piece of your own story with these ancient ones, you can leave a comment telling us where you're listening from. What corner of the modern world is watching these vanished worlds drift past? If you want to walk more of these timelines together, you can subscribe so the next story finds you again whenever you're ready to close your eyes and travel backward. And for those who feel moved to support this project a little more deeply, there is the option to join as a member here on YouTube. It's completely optional, never expected, but always quietly, sincerely appreciated. For now, though, the lights in these ancient landscapes are fading. Picture an evening on a long-lost plain somewhere in the late Jurassic. The last light of the sun is sliding under a bank of distant clouds. A herd of sauropods has already passed, their massive forms now only a memory in the settling dust. On the ground behind them, each footprint is a shallow pool, slowly filling with the first drops of night rain. In the quiet that follows, there is movement in a low, scrubby tree at the edge of the plain. A small, feathered animal shifts on a branch. It tilts its head, fluffs hollow bones that would not exist without the giants, and lets out a soft call into the cooling air. The rain deepens, the footprints darken, the plain grows still. Somewhere above that tree and above you, the same stars that watch the giants come and go are wheeling slowly on. You can let your own breathing match that slow turning. Let the last echoes of thunder fade into a distant, gentle murmur and rest.